Hello there, and welcome to Physics with William, where curiosity slows its breathing a little, and science is allowed to unfold at human pace. Tonight we are settling in with a particle that does not usually get top billing. It does not flash with the electric charge, it does not announce itself with sparks, and it rarely gets invited into popular science small talk in the way black holes or time travel do. It is the neutron, a quiet resident of the atomic nucleus, and despite its modest reputation, it turns out to be one of the most important and slightly puzzling things in the universe. Before we get into that, I would love to know where you are listening from. Are you under a blanket, at a desk, on a late train, pretending to be productive while actually thinking about particles? And what time is it for you right now? There is something I always enjoy about that. A conversation about the deep structure of reality, arriving in different rooms and different time zones, all at once, while the rest of the world carries on being gloriously unaware that we're about to spend a while thinking about a neutral little object hiding in the middle of matter. And if this sort of slow and soothing science is your kind of thing, do consider liking the video and subscribing. It helps this calm corner of the internet keep going, and it helps other people find their way here too. I cannot promise that learning about neutrons will improve your taxes, your posture, or your ability to fold fitted sheets, but it will at least give you a new appreciation for the stubborn little ingredients out of which everything solid is made. Now, at first glance, the neutron sounds almost disappointingly simple. Schoolbook simple even. The atom, we're told, has a nucleus made of protons and neutrons with electrons around the outside. The proton is positively charged, the electron is negatively charged, the neutron, true to its name, is neutral. End of story. Job done. But this is one of those cases where the simple version is a bit like saying that a cathedral is just a pile of stone with some windows. It is technically not wrong, but it leaves out the interesting part. Because the neutron behaves in a very strange way. Inside an atomic nucleus, it can sit there quite happily for immense stretches of time, contributing to the structure and stability of matter. Out on its own, though, separated from the company of protons and the tight, crowded environment of the nucleus, it does something rather dramatic. It dies. Not metaphorically, not in some vague philosophical sense. Quite literally, as a free particle, it changes into something else after a short while. Give a lone neutron a little under 50 minutes, and it will decay. It cannot simply remain itself forever. That is an odd thing to say about one of the basic components of matter. We like our fundamental ingredients to feel dependable. We prefer them to sit still and mind their business. Electrons do this very well. Protons, as far as we can tell, are spectacularly durable. Neutrons are more complicated. In one setting, they help build the world. In another, they fall apart. The same particle, stable in one place and unstable in another, which is exactly the sort of detail physicists hear and then immediately start reaching for notebooks. So tonight we are going to take the neutron seriously, not as the proton's quieter companion, not as the unlabeled grey ball in a textbook diagram. We are going to ask what it actually is, why it matters, and why it can survive so well in a nucleus while failing rather badly when left to fend for itself. And I think part of what makes that question so satisfying is that it seems so innocent at first. A neutron. What is a neutron? It sounds like the sort of thing one should be able to answer in a sentence. But the real answer takes us into the structure of atoms, the forces that hold nuclei together, the weird bookkeeping of nature, the meaning of stability, and the fact that the universe is not obliged to make its building blocks emotionally convenient for us. To see why the neutron is so peculiar, it helps to begin with the atom in the ordinary sense, not the intimidating one. Not as a cloud of equations or a wall of terminology, but as a tiny bound system that makes up the material world around you. The air, the table, your skin, the glass in a window, the metal in a spoon, all of it is built from atoms. Each atom has a nucleus at the centre, and in that nucleus live protons and neutrons. The number of protons tells you what element you're dealing with. 1 proton gives you hydrogen, 6 gives you carbon, 8 gives you oxygen, 26 gives you iron. In that sense, the proton gets to be the identity card. It tells the universe what kind of atom this is. The neutron plays a different role. It does not change the element by its presence alone, but it changes the character of the nucleus. It adds mass. It contributes to nuclear stability. It affects whether a nucleus is snug and durable or precarious and eager to transform. 2 atoms of the same element can have different numbers of neutrons, and then we call them isotopes. Chemically, they behave much the same because chemistry mostly cares about electrons and charge. Nuclear physics, though, cares very much indeed. A carbon atom with 6 neutrons is common and stable. A carbon atom with 8 neutrons is unstable and radioactive. Same element, different neutron count, entirely different mood. That already tells us something important. The neutron is not decorative. It is structural. It is one of the reasons nuclei can exist in the rich variety they do. If you imagine a nucleus as a crowded little gathering of positively charged protons that ought, by all rights, to dislike being jammed together, then the neutron is part of what makes that gathering possible. It helps apply the strong nuclear force without adding more electric repulsion. It is, in that sense, an excellent team player. It shows up, adds useful weight, contributes to the glue, and refrains from making the electrostatic argument worse. And yet this well-behaved nucleus helper has a private problem. Alone, away from the nucleus, it is not the lowest energy arrangement available to it. Nature, whenever it can, tends to drift toward arrangements that are more stable. Not morally better, not more noble, just more stable. Lower energy, easier to maintain, less strained. A free neutron is a bit like an object balanced awkwardly on a shelf edge. It can stay there for a little while, but it is not the preferred situation. Eventually it tips into a more comfortable state. In the neutron's case, that means turning into a proton, along with an electron and a ghostly particle called an antineutrino, which we will get to properly later on. The key point for now is simply this. A free neutron does not remain a neutron. If that sounds almost unfair, it is because our human intuition is built at the wrong scale. In everyday life, a thing tends to remain the thing it is unless something obvious happens to it. A chair stays a chair. A pebble stays a pebble. Even if it wears down over centuries, it does not suddenly become another object in a quarter of an hour because some internal rulebook has judged its existence mildly inefficient. Particles are not concerned with what feels fair to us. They obey the deep rules of interactions, conservation, and energy. The neutron does not ask whether it would be dramatic to decay. It simply follows what the laws of nature allow and what the balance of stability prefers. One reason this topic is so satisfying is that the neutron sits exactly on the line between familiar matter and strange physics. On the one hand, it is part of nearly every atomic nucleus in your body. You are full of them. On the other hand, if you isolate one and watch it in the right setting, it reveals that matter is not a collection of little billiard balls, but a world of transformations. Things can change identity. Mass differences matter. Stability depends on context. The universe is less like a box of fixed beads and more like a system of patterns that can hold together or come apart depending on the circumstances. There is also a nice historical irony here. For a long time, the neutron was not obvious at all. It had no electric charge, which made it much harder to detect than charged particles. Charged particles leave clearer traces. They can be steered by fields. They announce themselves more readily. Neutrons do not do that. They slip through matter in ways that make them deeply useful in some settings and annoyingly elusive in others. So even once people had begun to understand atoms as structured systems with smaller ingredients inside, the neutron remained hidden for a while, like a very important guest who had arrived early and then chosen to stand quietly near the back. That hidden quality suits the particle rather well. The neutron often turns out to be central without being obvious. It helps determine which nuclei are stable. It plays a major part in radioactive decay. It drives chain reactions in reactors because, lacking electric charge, it can get close to nuclei more easily than protons can. It is involved in the creation of many heavy elements in violent astrophysical events. Entire stars can collapse to the point where matter is packed so densely that neutrons dominate almost everything, producing neutron stars, objects so extreme that they sound as though science fiction got ahead of itself, and then physics reluctantly admitted that, no, actually this one is real. But before any of that, before stars and reactors and decay chains, there is a simpler puzzle worth keeping hold of. Why should a neutral particle exist at all inside the nucleus? Why is it needed? Why not just pack nuclei with protons and leave it at that? The answer begins with electric charge and force. Protons repel each other because they all carry positive charge. The more protons you try to squeeze into a small nucleus, the more that repulsion matters. Something stronger and shorter range has to overcome it, and that something is the strong interaction. Neutrons participate in that strong binding without adding extra electric repulsion. In a very real sense, they make complex nuclei possible. Without neutrons, the periodic table would be a sad and underachieving place. Hydrogen offers a useful exception, as it often does in physics. The most common kind of hydrogen has a nucleus consisting of just a single proton and no neutron at all. That is the simplest atom. It gets away with it because one proton does not need help dealing with repulsion from other protons. There are no other protons there, but once nuclei become larger, neutrons become increasingly important. Their presence helps buffer the proton crowd, not by acting like little cushions in any literal sense, but by contributing binding through the strong force. That is why so many stable nuclei contain both protons and neutrons, and why the ratio between them becomes an issue of balance rather than decoration. Now, if you're listening to all this and thinking that the neutron sounds less like a particle and more like a diplomatic compromise, I think that is actually not a bad instinct. The nucleus is a tense little place. Protons want to repel one another electrically. The strong interaction wants to bind nucleons together at very short range. Quantum rules govern which arrangements are allowed and favoured. The neutron arrives with no electric charge, useful mass and strong interaction credentials. It helps the nucleus exist. And yet it pays a price for its own internal structure, which means that outside this shared environment it cannot last indefinitely. In social terms, it is the friend who keeps the group stable at dinner, but becomes surprisingly fragile when walking home alone. This is where the neutron stops being merely a nuclear ingredient and becomes a clue. A clue that the particles we call basic in ordinary speech are not necessarily simple in their internal behaviour. The neutron is not elementary in the modern sense. It is made of smaller constituents called quarks, held together by gluons in a restless quantum system. That internal arrangement gives the neutron its properties, including the slight mass difference that becomes crucial when we ask why a free neutron decays while a proton does not. It is a reminder that neutrality is not emptiness. The neutron is not featureless because it has no net charge. Internally, it is a busy, structured, dynamic thing. And there is another reason the neutron deserves a gentler and more careful introduction than it often gets. It sits right at the intersection of permanence and change. Matter feels stable to us. The room does not flicker out of existence. The table is still there in the morning. The atoms in your body are not conducting visible acts of rebellion. And yet, underneath that calm surface, some of the pieces are only stable because they are in the right arrangement, in the right company, under the right rules. Pull one neutron out of that environment and time begins to matter in a different way. Suddenly the question is not just what it is, but how long it can remain itself. That makes the neutron a beautiful example of something physics teaches over and over again. Context matters. A thing can be stable here and unstable there. A process can be forbidden in one setting and common in another. What survives depends not only on what something is made of, but on what surrounds it and what alternatives nature permits. We are often tempted to ask for a single label, a final neat definition. What is a neutron? The better question, and the more revealing one, is what kind of thing is a neutron in the environments where it actually lives? So as we move further into this story, it will help to keep a few simple ideas in mind. First, the neutron is one of the key building blocks of atomic nuclei. Second, it has no net electric charge, which makes it behave differently from protons and electrons. Third, it is not stable forever when isolated. And fourth, that instability is not a side note. It is one of the most revealing facts about it, because it tells us that even the ingredients of matter are governed by deeper layers of structure and balance. And the strange part is that for a while, scientists had good reason to suspect something in the nucleus was missing, even before they could point to the neutron directly. The mass of nuclei did not quite fit a picture made only of protons and electrons. The charge worked one way, the mass another, and the numbers refused to settle down into a tidy story. There was something else in there, something electrically silent but physically significant. And once people began to hunt for it in earnest, the neutron was waiting, quietly, naturally, and with a rather important tale to tell. There is something slightly suspicious about a particle whose defining feature seems to be that it does not do the one thing people expect particles to do in beginner science lessons, which is carry some obvious charge and then behave accordingly. The proton turns up looking positive and fairly self-assured. The electron arrives negative and agile and impossible to ignore. The neutron, by contrast, sounds almost like an apology. It is neutral. It does not pull one way or push the other in any simple electrical sense. It appears, at first glance, to be the least dramatic member of the atomic household, a sort of background resident. Useful, perhaps, but not especially exciting. And that first impression is wonderfully misleading, because the neutron has one of the oddest reputations in physics. Part of that reputation comes from how it hides. Charge makes a particle easier to notice. Charged particles leave clearer trails. They respond to electric and magnetic fields. They can be bent, steered, trapped, slowed, and generally treated like unruly shopping trolleys if one has the right equipment and sufficient patience. A neutral particle slips past many of those tricks. It does not swerve in the same obvious way. It does not announce itself with quite the same theatrical flair. If the proton is the guest who arrives in a bright coat and the electron is the guest who knocks over a lamp while trying to sit down, the neutron is the one who somehow entered the room 20 minutes ago and is already making important life choices from the quiet corner by the bookshelf. That silence gave it a peculiar sort of mystique. Even the name feels restrained. Neutron, not blazing sphere of mystery, not chaos pellet, just neutron. As though someone discovered an object of immense importance and, in an admirable moment of understatement, named it by saying, well, it appears not to be charged, so that will do. Physics has always had a slightly uneven relationship with naming things. Sometimes it gives us grandeur. Quark has flair. Black hole certainly knows how to market itself. Then sometimes it gives us language that sounds like a village council has reluctantly approved a new bin collection schedule. Neutral particle, neutron. And yet behind that very plain name sits something surprisingly consequential. If you ask a person who has not spent much time around nuclear physics what they associate with neutrons, the answers tend to fall into two broad camps. One group vaguely remembers them as those things in the middle of atoms, which is not wrong, but does have the feel of remembering that Paris is in Europe and calling the matter settled. The other group has heard the word in more alarming contexts: nuclear reactors, radiation, bombs, neutron stars. The neutron, despite lacking electric charge, has acquired a rather charged reputation in culture. It sounds serious. It sounds faintly dangerous. It sounds like the kind of thing you should not lick, store in a jam jar, or discuss too confidently at a dinner party unless you're prepared to be corrected by a physicist with a very calm voice and a great deal of patience. This is one of the interesting contrasts about it. The neutron is quiet in one sense and notorious in another. Inside ordinary matter, it is one of the hidden supports of the world. Outside the nucleus, or in more extreme environments, it becomes involved in some of the most powerful processes we know. It can pass into atomic nuclei more easily than a proton can, precisely because it carries no electric charge. It can trigger transformations, it can help initiate chain reactions, it can contribute to the making of new elements in stars and stellar explosions. It can, in very large numbers, help define the structure of some of the densest objects in the universe. That is a rather impressive career for something often introduced in textbooks as the neutral bit in the middle. And neutrality itself can be deceptive. In everyday language, neutral sounds mild. It sounds uncommitted. A neutral person in an argument is trying not to take sides. A neutral paint colour is unlikely to start a family dispute. A neutral particle, though, is not passive in any deep sense. The neutron has no net electric charge, but that does not mean it lacks structure, influence, or consequence. It is not blank, it is balanced. And balanced things can be surprisingly complicated. Think of an ordinary object that looks calm from a distance, a pond on a still evening perhaps. Smooth surface, no fuss, almost insultingly peaceful. Come closer and there is movement everywhere. Tiny currents, insects touching the surface, plants underneath, mud settling, fish weaving between shadows. The stillness is real in one sense and completely misleading in another. The neutron is a bit like that. From far away it seems like a simple neutral particle. Up close, it is a dense little system with internal parts and internal tensions, and those details matter enormously. This is where its strange reputation really begins. In classical thinking, one might imagine that the neutral member of the atom would be the easy one. No charge, less trouble. But when physicists started understanding the nucleus properly, the neutron turned out not to be the lazy middle child at all. It was central to the entire question of why nuclei exist in the first place. Protons repel each other electrically. That is not a small inconvenience. If you tried to build nuclei from protons alone, the repulsion would become a serious problem very quickly. The strong interaction can bind nucleons together at short range, but the balance is delicate. Neutrons help enormously because they participate in that nuclear binding without adding more electric repulsion. They are like reinforcements who show up with useful tools and, crucially, without bringing extra drama. That is why the neutron earns a place in the nucleus beyond mere filler. It is not there to bulk out the numbers or make the atom look symmetrical. It contributes to stability. It helps determine whether a nucleus can hold together. It changes which isotopes are possible, which are common, which are unstable, and which decay away with varying degrees of impatience. If the proton gives an element its name, the neutron does a great deal to decide its temperament. Two nuclei with the same number of protons can behave very differently depending on how many neutrons accompany them. One may be perfectly content to remain as it is. Another may be quietly radioactive, waiting for its chance to rearrange itself into something more comfortable. That word comfortable is more useful in physics than it first sounds. Nature likes arrangements that are stable, and stability often means lower energy, less strain, less need for further rearrangement. A nucleus is not a static marble. It is a quantum system in which particles occupy allowed states, and the overall arrangement can be more or less favourable. Neutrons influence that favourability. Too few, and the nucleus may not hold together well. Too many, and it may become unstable in another direction. The right number can produce a remarkably durable balance. So the neutron is not just present, it is part of the negotiation. Even so, its public reputation is often shaped less by stable nuclei and more by what happens when neutrons are moving freely. And here the story becomes more curious. Because of its lack of electric charge, a neutron can approach atomic nuclei without being repelled in the way a proton would be. A proton trying to get near a positively charged nucleus faces an electrical barrier. The nucleus says very firmly, absolutely not. A neutron does not face that same barrier. It can get close. It can enter. It can be absorbed. And when that happens, the target nucleus may become excited, unstable, or prone to splitting. In reactors, this property is essential. Free neutrons can trigger fission in certain heavy nuclei, releasing energy and more neutrons, which can then continue the process. So the uncharged particle, the seemingly modest one, turns out to be precisely the tool that can slip past the front gate. This is one reason the neutron came to be associated with the more formidable side of nuclear physics. It is not that it is malicious, of course. Particles are gloriously free of moral ambition. But the neutron is effective. Its neutrality gives it access. In medicine, industry, research, and energy production, that can be useful. In weapons, it can be catastrophic. The reputation follows naturally. People hear neutron and think of invisible penetration, nuclear reactions, immense forces, things best handled by specialists in carefully marked rooms, which is all fair enough, though it can obscure the quieter and, in some ways, more beautiful truth that neutrons are also among the reasons ordinary matter is as rich and varied as it is. Another part of the neutron's reputation comes from its behaviour toward us in ordinary sensory terms, which is to say, none whatsoever. You cannot see a neutron. You cannot feel one passing by in any direct way. If a neutron beam goes through a material, what matters is how those neutrons interact with nuclei along the way. This can make neutron science feel slightly ghostly. Charged particles are easier to imagine because they fit older intuitions about sparks, currents, and forces. The neutron is subtler. It moves through matter with a kind of quiet decisiveness, and only occasionally reveals itself by what it changes. That can make it seem mysterious in a very specific way, not because it is beyond understanding, but because it does not perform its existence for us. And then there is the peculiar fact that the neutron is both common and, under the wrong conditions, temporary. Most of the neutrons you will ever think about are safely tucked inside nuclei. There they may persist for astonishing spans of time. Yet a lone neutron, wandering free, cannot survive indefinitely. It decays. This gives it a sort of double identity. In company, stable enough to help build the world. Alone, short-lived by particle standards. There is something almost literary about that, though physics itself is not trying to be literary. It is simply telling us that stability depends on circumstance. The neutron is one of the clearest examples of that lesson. This also helps explain why its reputation among physicists is a little more affectionate and a little more wary than one might expect. The neutron is useful, revealing, indispensable, and slightly awkward. It does not fit simple categories. It is not fundamental in the same sense as the electron. It is built from quarks. It is neutral overall but internally structured. It is stable in nuclei but unstable when isolated. It is hard to detect directly but deeply influential. It can help hold matter together and help tear nuclei apart. That is quite a collection of habits for one particle. You begin to see why it attracts a strange sort of respect. There is also a practical reason scientists learn to think carefully about it. Because the neutron does not carry electric charge, it became a powerful probe of matter. Send charged particles toward a material, and they may interact strongly with the electrons around atoms, getting diverted or slowed in ways that tell you something certainly, but also complicate the picture. Neutrons interact differently. They can penetrate into materials and scatter from atomic nuclei and magnetic structures, revealing details that other probes might miss or muddle. In that sense, the neutron has become one of the more refined investigative tools in modern science. It is not just something to be explained. It is something used to explain other things. Entire facilities are built to generate neutron beams so that scientists can study materials, magnets, molecules, proteins, and condensed matter with remarkable sensitivity. That is not the reputation most people meet first. Most people meet the neutron either in a school diagram or in a rather tense conversation about nuclear energy. But among researchers, it also carries the reputation of being incredibly informative. It is a particle that can tell you how a solid is arranged, how atoms vibrate, how magnetic order behaves, how a material changes under pressure or temperature. The quiet guest from the corner of the room turns out to have noticed everything. Its lack of charge also means it does not care much for electric boundaries. that dominate the lives of other particles. That makes it, from a certain point of view, socially unusual. Protons feel repulsion from nuclei. Electrons are guided and buffeted by electric fields all over the place. Neutrons simply do not respond in the same way. They are governed by other interactions and by their internal magnetic character, but their overall neutrality lets them travel routes that charged particles cannot. This can make them seem almost aloof, though aloofness is not quite the right word. Efficient, perhaps, indifferent to the obvious traffic signs. Of course, neutrality in the electrical sense does not mean the neutron is completely without external influence. It has mass, so gravity still applies, though at the scale of particle experiments, gravity is laughably weak and mostly irrelevant. It also has a magnetic moment because of the motion and arrangement of its charged constituents inside. That alone is a lovely reminder that net charge is not the whole story. The neutron is made of quarks, and those quarks do carry charge. Their charges add up to 0 overall, but internally they create structure. So even the phrase no charge needs a little care. It means no net electric charge. It does not mean empty. It does not mean featureless. It does not mean there is nothing going on. And what is going on is part of why the neutron cannot be treated as a simple indivisible bead. Inside it, quarks are bound by gluons in a restless quantum dance that does not lend itself to tidy little planetary pictures. The neutron is a composite particle, which means its properties emerge from the behaviour of smaller parts and the strong interaction that binds them. That internal arrangement gives the neutron its mass, its magnetic moment, and ultimately its vulnerability when left alone. The more physics learned about the neutron, the less it looked like a blank neutral sphere, and the more it looked like a delicately balanced quantum object that only seemed plain from a distance. This is true of many things in science, really. The simple version is often only simple because it is viewed from far enough away. A beach can look smooth from a cliff, and then turn out to be all shells, stones, ridges, footprints, and tiny dramas when you kneel down. The neutron in a schoolbook is a grey circle with a helpful label. The neutron in real physics is a dynamic hadron with a specific internal makeup, a particular mass, an unusual stability profile, and a remarkable ability to influence nuclear life. One is useful. The other is interesting. Ideally, one grows into the other. Its reputation also picked up a certain amount of confusion, simply because it arrived historically at a moment when atomic theory itself was becoming crowded and strange. Early models of the atom were revised repeatedly as new evidence came in. Electrons appeared. The nucleus was identified. Radioactivity complicated everything. Quantum mechanics arrived and politely informed everyone that the old visual habits would need to be abandoned. In that shifting landscape, the neutron became both a missing piece and a fresh source of complication. It helped solve puzzles about atomic mass and nuclear structure, but it also opened new questions about forces, decay, isotopes, and the deep architecture of matter. In other words, it improved the story by making it more true and therefore less simple. This is usually how progress behaves, rather annoyingly. One hopes for clarity and is rewarded with layers. The neutron offered clarity about why atomic nuclei were not just bundles of protons, with a few electrons awkwardly stuffed inside. That older picture had all sorts of problems. The neutron cleaned up the accounting beautifully. But once it was in place, physicists had to explain what the neutron itself was doing, how it contributed to binding, why free neutrons decayed, how nuclear transformations worked, and why some isotopes sat quietly, while others emitted radiation with almost impatient regularity. The particle with no charge was proving rather good at generating work. And then, of course, there is the reputation it has earned in the cosmos. Once you start talking about neutron stars, the neutron acquires an almost mythical air. Here is a particle so associated with the small and hidden that it can also dominate entire stars after the collapse of massive stellar cores. Matter becomes compressed to such extraordinary density that electrons and protons are forced into new arrangements and neutrons take over the bulk of the structure. The result is an object with the mass of a star packed into the size of a city. That is the sort of detail that permanently upgrades a particle S image. It is difficult to remain the boring one after that. Still, the most interesting part of its reputation may be the contradiction at the centre of it. The neutron is known as a stabilizer of nuclei, yet a free neutron is unstable. It is known as neutral, yet internally it is full of charged constituents. It is known as quiet, yet it can set off violent nuclear events. It is known as hidden, yet it tells us a tremendous amount about matter when used as a probe. The reputation is strange because the particle is strange, not in the sensational sense, but in the deeply satisfying scientific sense of something whose ordinary label conceals an unexpected amount of detail. If you imagine the early 20th century physicists peering into the atom with growing suspicion, it begins to make sense. They had charge accounted for only up to a point. They had mass accounted for only up to a point. They could see that the old bookkeeping was not working. Something neutral and weighty seemed to be lurking in the nucleus, doing essential work without showing itself in the more obvious electrical measurements. The reputation of the neutron, before it was even fully pinned down, was already forming. A hidden contributor, a silent necessity, the sort of thing that does not make a fuss but without which the numbers refuse to behave. And that is usually when physics gets interested, when the visible story is not enough, when charge says one thing and mass says another, when the nucleus seems too compact, too heavy, too stable or unstable in just the wrong places. The neutron earned its odd reputation because it sat exactly in that gap between what was seen and what had to be true. By the time experimentalists finally cornered it, they were not discovering a minor extra. They were finding the missing resident of the nucleus, the uncharged partner with an unexpectedly eventful life. And the trail that led to it began with those stubborn clues that refused to add up. And that hunt is one of those episodes in science that becomes more interesting the longer you look at it, because the neutron was not hidden in the sense of being impossibly rare or locked away at the edge of the universe. It was hidden by assumptions. It was hidden by the limits of the instruments. It was hidden by the fact that electric charge is much easier to notice than silence. In a way, the neutron was sitting in the nucleus the entire time, doing essential work, while generations of physicists kept circling around it with the scientific equivalent of saying there must be something else in there. But what exactly is it? To appreciate why the discovery took as long as it did, it helps to remember how strange the atom already seemed in the early part of the 20th century. People were not starting from a tidy, complete picture and then adding one final elegant detail. They were building atomic theory in stages, and each stage introduced both progress and fresh confusion. First came the realization that atoms were not indivisible after all. Electrons appeared on the scene. Then the nucleus was identified. Radioactivity made it clear that atoms could transform. Quantum theory began rearranging the furniture. So by the time the neutron was finally identified, physicists were already standing in a room full of half-solved puzzles, trying not to trip over any of them. At first, the nucleus itself was the great surprise. Before Ernest Rutherford and his collaborators carried out the famous scattering experiments, many people imagined the atom in a much softer way, with positive charge spread out and electrons embedded within it. Then came the gold foil experiment, in which alpha particles were fired at thin metal foil and a tiny fraction bounced back at large angles. That result was so startling because it suggested that most of the atom was empty space, with a dense concentrated nucleus in the middle. Suddenly the atom had a centre, a very small, very heavy, very positively charged centre. That was a huge step forward, but it immediately raised a practical problem. If the nucleus carried positive charge and contained most of the mass, what exactly was in there? The obvious answer was protons, and protons certainly belonged there. They supplied the positive charge. The trouble was that charge alone did not account for the mass. When scientists looked at atomic masses and compared them with atomic numbers, the numbers did not line up neatly enough for a nucleus made only of protons. Something was missing. For a while, one popular workaround was to imagine that electrons also lived inside the nucleus. That may sound odd now, but at the time it seemed like a tempting way to solve the bookkeeping. If you packed enough protons into the nucleus to explain the mass, then perhaps some nuclear electrons could reduce the overall positive charge to the value actually observed. It was a clever attempt, and it did at least try to satisfy the known facts. But it was also a rather uncomfortable arrangement. Tiny electrons somehow trapped inside an even tinier nucleus, contributing to charge balancing in a way that caused all sorts of theoretical headaches. Those headaches did not go away. In fact, they multiplied. Nuclear electrons created problems with quantum behavior, with spin, with statistics, and with the general sense that this picture was being forced to do jobs it was not naturally suited for. There were also clues from spectroscopy and nuclear properties suggesting that the old proton-electron model of the nucleus was not quite right. Physicists could feel that the structure underneath matter was resisting the explanation they were trying to give it. The numbers almost worked, but only almost. And in science, almost is often the first sign that something important has not yet been recognized. Isotopes added to the pressure. Once scientists understood that atoms of the same element could have different masses, it became even clearer that charge and mass were not telling the same story. Chemically, two isotopes of an element behaved almost identically, because chemistry is mostly about electrons. But their masses were different, which meant their nuclei were different. The nucleus, then, had to contain something more than just the minimal number of protons needed to define the element. There had to be another source of nuclear mass that did not alter the atomic number. At this stage, the neutron was already beginning to exist as a kind of shadow in the data, not yet as a cleanly established particle, but as the shape of a missing answer. Rutherford himself had even speculated about the possibility of a neutral nuclear constituent, something like a tightly bound proton and electron combination. That idea was not the same as the modern neutron, but it shows that the conceptual space for a neutral massive object had begun to open up. Scientists knew the nucleus was not fully understood. They knew mass and charge were being accounted for in awkward ways. They knew a neutral partner would solve several problems at once if only it could be shown to exist. What made that so difficult was the very property that would later make the neutron so useful. No electric charge means no straightforward response to electric fields. No easy bending in magnetic fields in the same obvious way charged particles can be bent. No bright sign saying "here I am." If you're searching for a charged particle, you can often trace its path more directly. If you are searching for a neutral one, you're usually forced to infer it from what it does to other things. That is a harder game. You're not looking for footsteps. You're looking for furniture moved in the night. Then came a series of experiments that brought the hidden resident of the nucleus much closer to the surface. In the early 1930s, researchers began bombarding light elements with alpha particles, which are energetic helium nuclei emitted by radioactive substances. One target in particular, beryllium, produced a very penetrating kind of radiation when struck by alpha particles. This was first studied by Walter Bothe and Herbert Becker, who observed that the radiation was unusually penetrating and, quite reasonably at the time, interpreted it as a very energetic form of gamma radiation. That interpretation made sense on the evidence then available. Gamma rays were known to be highly penetrating. The new radiation carried no obvious electric charge. It seemed plausible enough, but plausibility in physics has a shelf life, and this particular explanation began to wobble when other researchers looked more carefully at what the radiation was doing. Irene Joliot-Curie and Frédéric Joliot studied the same beryllium radiation and directed it at substances rich in hydrogen, such as paraffin wax. This produced a striking effect. Protons were being knocked out of the hydrogen-rich material with considerable energy. Now, if the incoming radiation were really gamma rays, those gamma rays would have needed absurdly high energies to account for the recoiling protons in the way observed. It was not impossible in the strictest sense, but it was starting to feel less and less like the neat answer. This was the moment when James Chadwick, working in Cambridge, saw the opening. Chadwick had been one of Rutherford's students and was exactly the sort of physicist you would want at a moment like this. Careful, sceptical, deeply familiar with nuclear problems, not especially interested in being impressed by an explanation just because it was convenient. He looked at the evidence and recognized that the gamma-ray interpretation was straining under the weight of the data. Something neutral seemed to be colliding with nuclei and transferring momentum in a much more direct particle-like way. The brilliance of Chadwick's work was not simply that he announced a neutron and everyone applauded. It was that he set up the problem in a clean enough way to show that a neutral particle, with a mass close to that of the proton, explained the observations far better than ultra-energetic gamma rays did. He bombarded beryllium with alpha particles, examined the resulting neutral radiation, and studied how it knocked protons out of hydrogen-rich substances and other nuclei out of other materials. By comparing the energies involved, he could infer that the radiation behaved as though it consisted of neutral particles with substantial mass. That mass was the crucial point. A massless or nearly massless radiation like ordinary gamma rays would not account for the observed recoils in the same straightforward way. A neutral particle with about the mass of a proton would. Once that possibility was taken seriously, the whole nuclear puzzle suddenly became much clearer. Here was the missing nuclear constituent, neutral in charge, comparable in mass to the proton, and therefore exactly the kind of thing that could sit inside nuclei adding mass without changing atomic number. Chadwick published the result in 1932, and the neutron moved very quickly from suspicion to accepted reality. That speed is worth noticing. Sometimes a scientific idea takes decades to gain traction after the key evidence appears. In this case, the field was ready. The problem it solved was so central and the experimental case so compelling that the neutron was adopted almost immediately. It helped that it fit into existing nuclear concerns with remarkable efficiency. The mass discrepancies made more sense. Isotopes made more sense. The need for nuclear electrons diminished. The whole picture became cleaner. There is something satisfying about discoveries like that, because they can look obvious in hindsight without having been obvious at all beforehand. Once the neutron was identified, one can be tempted to say, of course the nucleus contains protons and neutrons. Of course isotopes differ by neutron number. Of course a neutral massive particle explains the bookkeeping. But before Chadwick's interpretation, the evidence did not walk into the room wearing a badge and introducing itself politely. It came as indirect effects, awkward models, puzzling mass data, and a radiation from beryllium that refused to behave as expected. This is what people mean when they say the neutron was hiding in plain sight. The nucleus was full of them, but the methods of detection favoured charged things. Theoretical habits leaned toward proton-electron constructions. The decisive experiments had to arrive in a form that made the neutral particle unavoidable. In a sense, physicists had been living beside the consequences of neutrons for years before they could see the neutrons themselves. And there is another quiet lesson in the story. Discoveries are often collective even when one name becomes the headline. Rutherford helped establish the nuclear picture and speculated about neutral constituents. Bolter and Becker observed the penetrating radiation from beryllium. The Joliot-Curies showed how that radiation could eject energetic protons from paraffin. Chadwick recognized what interpretation fit the evidence best and demonstrated it convincingly. The neutron was not found by one person staring dramatically into the distance and suddenly knowing. It emerged from a chain of experiments, questions, corrections, and the willingness to doubt a reasonable explanation when it stopped being reasonable enough. That kind of scientific progress is less cinematic than the lone genius myth, but much more reliable. One experiment reveals a phenomenon, another sharpens it, a third exposes a contradiction. Then someone with the right experience sees that the old explanation is becoming too expensive to maintain. The new idea arrives not as a thunderclap, but as relief. So that is what has been missing. Once the neutron entered the picture properly, nuclear physics changed pace. The nucleus was no longer imagined as an overstuffed bundle of protons awkwardly balanced by internal electrons. It became a system of protons and neutrons, soon called nucleons, held together by strong forces that were clearly more subtle than simple electrical attraction and repulsion. This opened the door to better models of nuclear structure, radioactive decay, and reactions. It also prepared the ground for later developments in particle physics, where the neutron itself would turn out not to be elementary after all. That last point is worth lingering on because it is almost mischievous. For years, the neutron was the missing piece needed to make the nucleus sensible. Then, once it had been securely installed as part of the answer, physicists eventually learned that the neutron itself was another composite object, with its own internal structure and its own unanswered questions. Science has a habit of solving one mystery by revealing a smaller, more inconvenient mystery tucked neatly inside it. Still, the discovery in 1932 genuinely was a turning point. Chadwick received the Nobel Prize a few years later, and rightly so. The neutron was not merely another particle to add to a growing list. It reorganized the atom. It clarified why nuclei have the masses they do. It explained isotopes naturally. It changed how researchers thought about nuclear reactions. It helped make sense of radioactive processes and later became central to both nuclear fission and the study of matter at deeper levels. And yet the charm of the discovery story is that it never feels flashy. The neutron entered physics almost in character, quietly, indirectly, through recoil measurements and awkward data analysis, through a problem about what beryllium was emitting when struck by alpha particles, through the failure of a respectable gamma-ray explanation. It was discovered in a way that suited its personality, not by shouting, but by refusing to fit the wrong story. It is also one of those cases where the phrase seeing is misleading. Nobody looked through a microscope and spotted a neutron sitting in a nucleus with a tiny neutral expression. What they saw were effects, recoils, penetration, energy transfers. What they recognized was pattern. If the radiation were gamma rays, the numbers became implausible. If the radiation were neutral particles with proton-like mass, the puzzle relaxed into place. Science often works like this. You do not always meet the object directly. Sometimes you meet the world behaving differently because the object is there. That may be why the neutron story remains so satisfying to tell. It captures something honest about physics. The universe is not obliged to reveal itself in the form most convenient to our senses. It gives clues in fragments. It lets assumptions linger until they become uncomfortable. It rewards patience more often than spectacle. And when the right answer finally arrives, it can feel both surprising and embarrassingly overdue. By the early 1930s then, the nucleus had gained its missing resident. The atom was no longer just a positively charged core with complications stuffed inside it. It had a more balanced architecture. Protons set the identity. Neutrons added mass and stability. Electrons remained outside the nucleus where they made much more sense. The bookkeeping improved. The theory improved. The questions naturally did not stop. Because finding the neutron answered one problem only to pose another very quickly. It told physicists that a neutral massive particle lived in the nucleus. Fine. But what kind of particle was it really? Was it simply a proton and an electron bound together after all? Was it fundamental? Why did it behave the way it did? Why was it stable in nuclei but not when isolated? And what exactly inside this apparently modest neutral object gave it such an important role in the structure of matter? That is where the story naturally moves next, because discovering the neutron is one thing, but understanding what sort of thing has actually been discovered is another matter entirely. And that is where the picture becomes much more interesting, because once the neutron had been identified as a real particle in the nucleus, physicists could no longer be satisfied with simply saying that it was the neutral companion of the proton and leaving the matter there. That description was useful as far as it went, but it only answered the most basic question. It told you where the neutron belonged in the atom and what role it seemed to play in charge balance and mass. It did not tell you what sort of thing a neutron actually was. It did not tell you whether it was simple or composite, whether it had parts, or why it behaved the way it did. And this is often the moment when science becomes more demanding in the most rewarding possible way. The first answer clears the fog just enough to reveal that a much deeper answer is now required. For a while, one tempting idea was that the neutron might literally be a proton and an electron bound tightly together. That had a certain rough appeal. A proton carries positive charge, an electron carries negative charge. Put them together and perhaps one gets a neutral object with about the right mass. It sounds neat in the way many early scientific ideas do when they are trying very hard to make peace with incomplete evidence. But nature is not always impressed by neatness. As physicists looked more carefully, that simple picture began to fail. It did not fit the quantum properties of the neutron properly. It created difficulties with spin and magnetic behavior. It also treated the neutron as though it were just a little electrical marriage of convenience, which turned out to be far too simple for what the particle really is. What we now understand is stranger and more satisfying. A neutron is not a proton plus an electron hiding in the same coat. It is a hadron, a particle made of quarks, held together by the strong interaction. More specifically, it belongs to a family called baryons, which are built from 3 quarks. In the neutron, those 3 quarks are arranged as 1 up quark and 2 down quarks. That combination gives the neutron its overall electric neutrality. The up quark carries a positive fractional charge. Each down quark carries a negative fractional charge. Add them together and the total comes out to 0. So when we say the neutron has no charge, that does not mean it contains nothing charged inside. It means the internal charges balance exactly. This is a very important shift in perspective. The neutron is not empty of electrical character, it is electrically balanced. That may sound like a small difference, but it changes the whole feel of the particle. It means the neutron is not a blank neutral bead, it is a structured object with internal constituents that each carry their own properties. If you could somehow look inside it, you would not find a featureless little ball of neutrality. You would find charged quarks in motion, bound together by gluons, with the entire object held in a dynamic quantum state that is far more active than the old schoolbook image suggests. And that image really does deserve retiring. For a very long time, people were taught to picture protons and neutrons as tiny solid spheres, like marbles packed into the atomic nucleus. That picture is understandable because it gives beginners something to hold on to. The trouble is that it is deeply misleading if taken too seriously. A neutron is not a miniature billiard ball with a smooth little surface. It is not a hard bead with a tidy interior. It is a quantum object. Its quarks are not little peas rattling around inside a shell. They exist as part of a system governed by quantum chromodynamics, the theory that describes the strong interaction. The gluons that bind the quarks are not passive glue in the household sense. They are active carriers of the interaction, and the whole interior of the neutron is better thought of as a restless field system than a static mechanical assembly. This makes the neutron harder to picture, but also more real. The universe is not under any obligation to organize itself into images that would sit nicely in a childish wooden toy box. At the scale of quarks and gluons, ordinary intuition begins to lose its grip. What matters are the properties, the allowed states, the ways the constituents interact, and the measurable consequences of those interactions. The neutron has mass, spin, magnetic character, and a certain size in the sense that experiments can probe how its charge distribution and matter distribution are arranged. But all of these emerge from a lively and complicated internal world, not from a tiny rigid lump. One of the great surprises of modern particle physics is that most of the mass of the neutron does not come simply from adding up the masses of its 3 quarks in some straightforward way. The quarks do have intrinsic masses, yes, but those masses are only a small fraction of the neutron's total mass. Most of the neutron's mass arises from the energy of the strong interaction itself, from the motion of the quarks and the gluon fields that bind them together. This is one of the most striking examples of something that physics teaches at the deepest level, which is that mass is not always just a count of ingredient masses. It can emerge from energy bound up in interactions. The neutron is heavy not merely because it contains things with mass, but because the dynamic energy of its interior contributes enormously to what the neutron is. There is something almost wonderfully rude about that from the point of view of common sense. We like the idea that an object weighs what its ingredients weigh, more or less. But the neutron says no, that is not the whole story. The binding, the motion, the energy of the fields all matter. In the tiny world inside a baryon, the relationship between parts and whole is not simple arithmetic. It is a full quantum negotiation. This internal structure also explains why the neutron has a magnetic moment, even though it has no net electric charge. That fact puzzled people when particles were imagined too simply. A neutral particle ought, one might think, to be magnetically uninteresting. But once you know the neutron contains charged quarks, moving in a bound state, the existence of magnetic character makes much more sense. Internal charge distribution and motion can produce magnetic behavior, even when the total charge sums to zero. It is rather like having a household budget that balances to exactly nothing at the end of the month while still containing a great deal of frantic movement in the middle. Zero in the total line does not mean nothing happened. The neutron also has spin, which is one of those quantum properties that is easier to use than to picture. It is not literally a little ball spinning like a planet or a top, although early language can make it sound that way. Spin is a built-in form of angular momentum carried by quantum particles. The neutron has spin 1/2, just like the proton and the electron. This matters because spin influences how particles behave in quantum systems, how they combine, how nuclei are structured, and what states are allowed. The neutron is not merely present in the nucleus as added weight. It brings quantum personality with it. Its spin participates in the architecture of matter. Now, when people hear that a neutron is made of one up quark and two down quarks, they sometimes imagine that this solves the problem in a clean and final way. There it is then, they think. We have opened the box and found the pieces, but even that statement, true as it is only the beginning. Because the inside of the neutron is not just three quarks sitting quietly in assigned seats, like respectable passengers on a train. The actual interior includes a seething quantum environment in which gluons are continually exchanged and in which additional quark-antiquark pairs can briefly appear as part of the particle C full internal structure. The neutron has 3 valence quarks that define its basic identity. Yes, but around and among them there is a far richer scene than the tidy phrase 3 quarks might suggest. That is part of what makes hadrons so fascinating. They are not simple containers. They are bound states of the strong interaction, and the strong interaction is powerful, messy, and deeply non-linear. Gluons themselves carry the very charge associated with the strong force, which means they can interact with one another as well as with quarks. This leads to a remarkably intense internal world. The neutron is, in a sense, a stable pattern formed within that world, a particular durable arrangement of energy and fields that behaves as a particle with definite properties. Calling it a particle is correct, but one should not let that word suggest a tiny pebble. It is more like a persistent quantum knot than a grain of dust, and yet for all this internal activity, the neutron behaves with enough consistency that we can describe it in clear ways. It has a definite mass, slightly greater than that of the proton. That small difference matters enormously. If the neutron were lighter than the proton, the world would look very different. Hydrogen would not behave the same way. Ordinary nuclei would not be built in the same pattern. The existence of chemistry as we know it would be altered in ways that are not small or charming. The fact that the neutron is just a little heavier than the proton is one of those details that can sound trivial until one realizes that an enormous amount of familiarity depends on it. This slight extra mass is tied to the internal quark content and the details of the strong interaction. The up and down quarks are not identical. Their masses differ, and the way they combine inside protons and neutrons leads to a small but crucial mass difference between those two particles. In the proton, the quark content is 2 up quarks and 1 down quark. In the neutron, it is 1 up quark and 2 down quarks. That change sounds minor when spoken quickly. 1 of this, 2 of that, instead of 2 of this, 1 of that. But in particle physics, minor changes in composition can have universe-sized consequences. The neutron ends up just heavy enough that, when free, it can decay into a proton and other particles. The proton, being lighter, does not reverse that process under ordinary conditions. This is one reason the proton is so durable and the free neutron is not. Inside the neutron, then, there is a tension between sameness and difference. It is closely related to the proton. They are like siblings in the particle family, similar in mass, identical in spin, both made of 3 quarks, both subject to the strong interaction in roughly parallel ways. Yet one has net positive charge and remarkable stability, while the other is neutral overall and only stable under the right conditions. The difference comes down to the details of their internal composition and to the weak interaction, which allows one quark flavour to change into another under certain conditions. That process lies behind neutron decay, which we will take up more fully later, but it begins with the fact that the neutron's interior is not frozen. Its identity is maintained by quantum rules, not by a rigid classical shell. It is also worth pausing over the word inside itself, because in ordinary speech it can smuggle in misleading ideas. When we say what a neutron really is inside, we do not mean there is a neat little hollow chamber, and we have merely opened the lid. There is no sharp mechanical boundary in the old-fashioned sense. The neutron has a spatial extent, yes, and experiments can probe its structure, but its constituents are described by quantum fields and probability distributions. The quarks are confined, which means they cannot simply be plucked out and observed in isolation, in the way one might remove raisins from a bun. The strong interaction grows more stubborn as quarks are pulled apart, a feature known as confinement. In practice, trying to isolate one quark from a neutron does not give you a lonely quark sitting on a tray. It gives you new hadrons forming from the energy involved. Nature refuses to let quarks roam free under ordinary circumstances. That fact alone is astonishing. The neutron is made of quarks, yet quarks are never casually seen wandering about on their own. They exist confined within composite particles such as protons and neutrons and various other hadrons. So the neutron is a kind of compromise between visibility and concealment. It can be observed as a particle in its own right, measured, scattered, stored for short periods, used in experiments. But the deeper layer inside it remains hidden in a specific way. We infer and probe that layer with great sophistication, yet we do not simply open a neutron and pour the quarks into separate labelled jars. This confinement is not a side detail. It is one of the deepest characteristics of the strong interaction. The very force that makes nuclei possible through residual effects at one level is also what binds quarks into hadrons at a more fundamental level. In a broad sense, the neutron exists because the strong interaction permits a stable bound state of 3 quarks in this particular arrangement. Without confinement and strong binding, there would be no neutron in the form we know. There would be no proton either, and ordinary matter would be impossible. So when we ask what a neutron is inside, we're really asking about one manifestation of the architecture that makes matter itself possible. Another useful way to think about the neutron is not as a thing with pieces glued together, but as a state the universe allows. That might sound abstract at first, but it becomes practical very quickly. The neutron is a permitted stable bound state under the strong interaction. Its quark content, spin, mass and other properties define that state. The proton is another closely related state. Neither is merely an arbitrary pile of ingredients. Each is a particular allowed configuration with its own measurable signature. This way of thinking helps because it avoids the trap of imagining the neutron as a miniature machine assembled from tiny classical components. It is better understood as a quantum object with internal structure that is inseparable from the interactions that define it. Even its apparent neutrality has layers. Experiments indicate that the neutron has a non-uniform internal charge distribution. Although the total charge is zero, the positive and negative contributions are not smeared uniformly in a bland, featureless way. The internal arrangement has shape and detail. Different regions of the neutron can contribute differently to its electromagnetic properties. Again, neutrality is not emptiness. It is a finely balanced internal arrangement, and there is something quietly profound in that. The neutron helps build the solid world while being itself a dynamic balance of deeper ingredients. It is one of the supports of matter, yet it is not made of simple solidity. It is made of motion, interaction, and structure that only settle into something stable because the underlying rules allow them to. That tells you something larger about reality. The stable things around us are often made from deeper patterns that are anything but still. This is also why the neutron is so much more than a bookkeeping entry in the nucleus. It is not there merely to fill a mass gap next to the proton. It has its own identity, its own internal architecture, its own relationship to the strong and weak interactions. Once 20th century physics reached the point of seeing that protons and neutrons were not elementary, the neutron became newly interesting all over again. The old nuclear mystery had been solved by discovering it. The newer particle mystery deepened by opening it up conceptually. By then, high-energy experiments and the development of quark theory made it possible to explain hadrons in a much more unified way. Protons and neutrons could be understood as part of the same family, distinguished by their quark content. This brought order to what had previously seemed like a growing zoo of strongly interacting particles. It also connected the neutron to a deeper framework in which matter is built not from dozens of unrelated little pellets, but from a smaller set of fundamental fields and interaction rules. That was an enormous conceptual victory. It turned the neutron from a puzzling nuclear resident into a comprehensible composite object, even if comprehensible here still leaves plenty of room for awe. Because the interior of the neutron remains one of those places where human intuition has to learn humility. We can measure scattering patterns, we can model quark distributions, we can calculate aspects of hadron structure with extraordinary precision using powerful theory and computation. But none of this turns the neutron into a simple picture. The more honestly one describes it, the less it resembles the classroom marble and the more it resembles a tightly bound quantum storm with a stable public identity. And perhaps that is the best way to hold the idea in mind as we continue. A neutron is a real particle, measurable and central to the structure of atoms, but inside it is a composite hadron made of quarks, held together by gluons, carrying mass largely from internal energy, possessing spin and magnetic character despite no net charge, and existing as a confined quantum state rather than a tiny solid bead. It is both more concrete and more strange than the older picture allowed. Once you see that, the next question almost asks itself. If the neutron is such a delicately structured object, so close to the proton and yet slightly heavier, so stable in the nucleus and so vulnerable outside it, what exactly keeps that balance from failing? What is it, at the deepest practical level, that allows this particle to exist at all, and then under the wrong conditions to stop existing as itself? That balance turns out to be far more delicate than the old classroom picture ever suggests. Once you learn that a neutron is made of 3 quarks, it is very tempting to imagine that the mystery has been neatly packed away. 3 quarks, there we are, problem solved. Everyone may go home and put the kettle on. But this is one of those places where the first clear answer is only the doorway to a better question. Because the important part is not just that the neutron contains 3 quarks. It is that those 3 quarks are arranged in a way that makes the neutron remarkably similar to the proton, and yet not quite the same, and that tiny difference is enough to shape an enormous amount of the universe. The neutron and the proton are, in many ways, near twins. They belong to the same family, they have almost the same mass, they share the same spin, they live side by side in atomic nuclei. They respond to the strong interaction in closely related ways. If you met them on paper for the first time, you might assume they were simply two versions of the same basic idea. And in a sense they are. The proton is made of 2 up quarks and 1 down quark. The neutron is made of 1 up quark and 2 down quarks. That is the swap. 1 quark changes places, and suddenly the result is a different particle with different charge and a different fate. There is something almost rude about how much depends on so small a change. It is the sort of thing that makes one suspect the universe enjoys understatement. You replace 1 up quark with a down quark, and the particle that results is no longer positively charged but neutral overall. It is no longer the stable anchor of ordinary hydrogen. It becomes a particle that can sit quietly inside nuclei for immense stretches of time, but cannot survive for long on its own. Chemistry, nuclear stability, radioactive decay, the abundance of elements, all begin leaning on this quiet difference. One changed ingredient, and the script of matter shifts. To understand why, it helps to slow down and look carefully at what those quarks are bringing to the arrangement. The up quark carries a positive 2/3 unit of electric charge. The down quark carries a negative 1/3. Put 2 up quarks and 1 down together, and you get a net positive charge, which is the proton. Put 1 up quark and 2 down quarks together, and the total comes out to 0, which is the neutron. That much is often stated quickly, almost as a piece of bookkeeping, but it is worth lingering over because it means the neutron is balanced rather than blank. Its neutrality is an internal compromise. Positive and negative contributions cancel precisely. That already makes it less like a simple uncharged pellet, and more like a carefully arranged household, where 3 very opinionated residents somehow manage to keep the electricity bill at exactly 0. But charge is only part of the story. The deeper reason the neutron is delicate lies in the fact that these quarks are not sitting passively inside it like beads on a tray. They are held together by the strong interaction, which is ferociously powerful at very short distances. This interaction is carried by gluons, and gluons do not behave like gentle bits of tape keeping a package shut. They are active participants in a very intense internal system. The quarks are confined, the gluons interact, energy circulates, and the neutron exists as a stable pattern within that bustle. The same is true of the proton. Both particles are built in a region where the strong interaction is doing most of the heavy lifting. That is why the proton and neutron are so similar in mass, despite their different quark compositions. The masses of the individual quarks are only a small part of what either particle weighs. Most of the mass comes from the energy bound up in the motion of quarks and gluons and in the strong interaction itself. So when we compare neutron and proton, we are not comparing 2 little bags with different numbers of identical pebbles. We are comparing 2 dynamic quantum systems that are almost the same and yet not exactly. Their closeness matters, and their difference matters even more. If the strong interaction were the only thing that counted, the proton and neutron would be even more alike than they are. In many respects, the strong interaction treats the up and down quarks as nearly interchangeable. Not perfectly, but nearly. That near symmetry is part of why protons and neutrons form such a natural pair in nuclei. From the point of view of the strong interaction, they are siblings with a close family resemblance. But the universe has other rules in play. The up and down quarks do not have exactly the same mass. Their electric charges are different. Electromagnetic effects matter, and the weak interaction exists, which means one kind of quark can under the right conditions change into another. It is this combination that makes the balance delicate rather than dull. The neutron ends up slightly heavier than the proton, not by much, but enough. Enough that when a neutron is free, with no nucleus around it to complicate the accounting, it can lower its energy by turning into a proton. This is not because the neutron is badly designed. It is because the proton sits a little lower in the hierarchy of available states. The neutron is like a coin balanced on edge compared with one lying flat. It can stand there for a while, but the arrangement is not the easiest one available. Nature notices, and this is where the phrase delicate balance really earns its keep. The neutron is not wildly unstable. It does not vanish the instant it appears. It survives long enough to be studied, to be used in experiments, to play major roles in nuclear and cosmic processes. Inside nuclei, it can be effectively stable for times vastly longer than human history, yet this same particle, built from only a slight rearrangement of quark content compared with the proton, is perched close enough to a lower energy possibility that the weak interaction can eventually tip it over. The balance is strong enough to sustain matter and subtle enough to permit change. There is something deeply instructive in that. We often imagine that the basic building blocks of reality must be either absolutely stable or obviously unstable, like bricks on one hand and fireworks on the other. But the neutron refuses those neat categories. It is more like a very well-made object that depends on context. In the nucleus, it fits beautifully into the overall arrangement. On its own, it carries just enough extra mass, just enough internal difference, that another outcome is preferred. This is not a flaw in the neutron. It is a lesson in how nature defines stability. The weak interaction is especially important here because it allows one flavour of quark to become another. That sounds like the sort of sentence one should not say too casually, but particle physics is full of casually astonishing facts. Inside a free neutron, one of the down quarks can transform into an up quark through the weak interaction. Once that happens, the quark content shifts from 1 up and 2 down to 2 up and 1 down, which means the neutron becomes a proton. In the process, an electron and an antineutrino are produced as well. Later we will follow that decay in more detail, but for now the essential point is that the neutron contains within it the possibility of becoming its slightly lighter sibling. That possibility depends on the mass difference being just right. Too small, and the process would not unfold the way it does. Too large, and the consequences for nuclei and element formation would be dramatic. This is one of those moments in physics where a tiny numerical fact casts a very long shadow. The neutron is only a little heavier than the proton, but that little is everything. It means free neutrons decay, but protons do not reverse the process under ordinary conditions. It means hydrogen, with its lone proton, can exist as the simplest stable atom. It means neutrons can serve in nuclei without replacing protons as the basic stable residue of ordinary matter. So much of the universe hangs on a difference that is small enough to sound almost petty, and yet delicate does not mean weak in the ordinary sense. The neutron is not fragile the way a soap bubble is fragile. Internally it is held together by the strongest interaction in nature. Its quarks are tightly confined. Pulling them apart directly is not an option. What is delicate is the balance of its identity relative to nearby alternatives. The neutron is robust as a hadron and conditional as a free particle. Those two facts sit together quite comfortably once you stop expecting matter to behave according to common sense categories. A useful way to think about it is to separate two different questions. One question is whether the neutron holds itself together as a bound state of quarks. The answer is yes, very effectively. The strong interaction sees to that. The other question is whether the neutron is the lowest energy particle available with its overall properties under the circumstances. The answer, when it is free, is no. The proton is slightly lighter, and the weak interaction provides a route from one to the other. So the neutron is internally secure and externally negotiable. It is not falling apart because its quarks are escaping. It is changing identity because another allowed arrangement is favoured. This distinction matters because it prevents a very common misunderstanding. People sometimes hear that a free neutron decays and imagine the neutron as somehow loosely assembled, as though the whole thing were held together with wishful thinking and academic optimism. In fact, the opposite is true. The neutron is a perfectly real, tightly bound hadron. Its decay is not evidence of poor construction. It is evidence that the laws of nature permit quark flavour to change and that the resulting particle is slightly lighter. That is a subtler and much more interesting story than mere disintegration. There is also an appealing symmetry in how the proton and neutron work together. The proton carries the positive charge that defines the element. The neutron adds mass and binding without extra electric repulsion. They are close enough to belong naturally in the same nuclei. but different enough that each serves a distinct role. The proton gives matter identity. The neutron gives it options. Without protons, there would be no familiar atoms. Without neutrons, the heavier nuclei would mostly fail to hold together. Their closeness is what makes the nucleus possible. Their slight mismatch is what makes the nuclear world varied instead of monotonous. And the mismatch really is slight. If you were allowed to view matter with some fantastical sensitivity and compare a proton and neutron side by side, you would not be looking at opposites. You would be looking at near relatives, almost mirror-like in their overall size and structure. The main swap is that one quark has changed type, but that tiny shift affects charge, mass, magnetic properties, and stability. It is like changing one musician in a trio and discovering that the whole sound of the piece changes from a bright daytime tune to something more evening in character. Similar instruments, similar arrangement, entirely different mood. The reference script has a fondness for the ordinary world, so it is worth saying this plainly. Every solid thing around you depends on this subtlety. The carbon in your body, the oxygen in the air, the calcium in bones, the silicon in glass, the iron in blood and stars. All of it reflects a world in which protons and neutrons are close enough to bind together and different enough to matter. If the neutron were much heavier, many nuclei would be harder to build or easier to lose. If it were lighter than the proton, ordinary hydrogen would no longer be the simple foundation it is. Stars would live different lives. Chemistry would be altered before it ever had a chance to become familiar. The ordinary world has tucked inside it a very particular quark arrangement that happens to work. This also explains why particle physicists are so attentive to small differences. In everyday life, a tiny mismatch can be ignored. A slightly crooked picture frame is tolerable. A biscuit that is 1 millimeter smaller than expected is not usually the end of civilization. In fundamental physics, tiny differences can decide whether a process happens at all. They can determine which particles survive, which nuclei form, and what kind of long-term structure the universe allows. The neutron and proton are one of the clearest examples of that principle. Nature does not need dramatic contrast to produce dramatic consequences. Sometimes all it needs is one quark swapped and a little extra mass. Then there is the question of why the neutron does not simply decay all the time everywhere. If the proton is lighter, why are neutrons not perpetually scrambling to become protons even inside nuclei? The answer, which we'll ease into more fully next, is that the nucleus changes the rules of what is energetically favourable. A neutron inside a nucleus is not an isolated particle making decisions alone. It is part of a many-body system. The total energy of that system depends on the arrangement of all the nucleons together. In some nuclei, converting a neutron into a proton would make the whole nucleus less favourable, not more. In others, it can happen and does happen, producing radioactive decay. Stability is no longer about the neutron by itself. It is about the household budget of the entire nucleus. This is why the neutron feels so context-sensitive. Free, it has one set of options. Bound in a nucleus, it has another. The particle itself has not become a different species in some magical sense. Its internal quark structure remains what it is, but the energetic landscape around it changes. The cost and benefit of becoming a proton are no longer judged in isolation. They are judged against the total nuclear arrangement, and that changes everything. So when we say the neutron is delicately balanced, we mean several things at once. We mean that its internal quark arrangement is very close to the proton but not identical. We mean that the mass difference is small but decisive. We mean that the strong interaction holds it together firmly while the weak interaction gives it a path to become something else. We mean that its fate depends not only on what it is, but where it is. And we mean that the whole visible world sits downstream of that subtle balance in a way that is almost absurdly easy to overlook. There is a quiet beauty in that, though not the dreamy kind one says just to sound thoughtful. It is the practical beauty of a system that works because several influences are finely matched. Too much one way and ordinary matter changes beyond recognition. Too much the other way and nuclei become anemic or impossible. The neutron lives in that narrow middle ground where similarity and difference coexist. It is nearly a proton, but not quite. It is neutral, but not empty. It is strongly bound, but not absolutely final. It is one of those physical objects that seems simple only until you notice how carefully everything about it is tuned relative to everything else. And once you do notice, the next step is hard to avoid, because if the neutron is this close to the proton, this dependent on context, this sensitive to the company it keeps, then the nucleus begins to look less like a pile of particles and more like a kind of home. Not a cozy home exactly, since it is still a crowded quantum environment held together by powerful interactions and a fair amount of mutual tension, but a place where the neutron can remain itself in a way it cannot quite manage alone. That is really the heart of it. The atomic nucleus feels like home to the neutron because home, in physics, is not sentiment. It is the place where a thing can remain what it is without being nudged toward becoming something else. A free neutron exists in a world where there is a slightly easier arrangement available. It can become a proton and lower the total energy. Inside the nucleus, however, the rules are no longer about a single particle in isolation. They are about the collective arrangement of many particles bound together in a tightly organized system. Once the neutron joins that system, its identity is judged in relation to the whole structure, and in many cases that structure strongly prefers to keep it exactly where it is. This is one of the most important shifts in all of nuclear physics. If you stay too focused on the neutron as an individual object, you miss the reason it behaves so differently when bound in matter. Inside the nucleus, the neutron is not just sitting in a box waiting to decay out of habit. It is participating in a balance of forces, energies, and allowed quantum states that can make remaining a neutron the better option. That is why the nucleus feels like home. It is not because the neutron becomes a fundamentally different particle there. It is because the environment changes what counts as stable. That word stable, once again, is doing a great deal of work. In ordinary life, stable suggests something solid, unmoving, secure. A stable chair does not wobble, a stable bridge stays up. In nuclear physics, stability means that a configuration does not have an energetically favourable path to rearrange itself under the interactions available to it, or at least not one that happens easily. A neutron inside a nucleus can be stable because changing it into a proton would not improve the nucleus overall. In fact, it might make the nucleus less favourable, more crowded electrically, or impossible in terms of the allowed quantum arrangement. So the neutron remains a neutron, not because the weak interaction has stopped existing, but because the full system no longer wants the change. This matters because protons and neutrons do not merely pile into the nucleus like stones tipped into a bucket. The nucleus is a quantum system with structure. The nucleons occupy states. They interact through what is often called the residual strong force, which is the effective nuclear attraction between protons and neutrons, and between neutrons and protons at short range. This attraction is what overcomes the electrical repulsion between protons and allows the nucleus to exist at all. The neutron is especially valuable in that environment because it contributes to the binding without adding more positive charge. It strengthens the household without increasing the argument at the door. That is a useful way to think about it. Protons are essential because they define the element, but too many protons close together create increasing electric repulsion. Each proton pushes against the others. The strong interaction can overcome that, but only up to a point and only with the right balance of participants. Neutrons help by adding strong interaction support without contributing to the proton crowding in the electrical sense. They are, in a very practical way, excellent nucleus builders. They add cohesion without adding electrostatic trouble. If the nucleus were a very cramped committee meeting, the protons would all arrive with loud opinions and mutually incompatible seating preferences, while the neutrons would show up carrying the biscuits and quietly make the entire gathering possible. This is why even the simplest patterns of nuclear stability already reveal the neutron-s importance. Light nuclei often remain most stable when the number of protons and neutrons is roughly balanced. As nuclei grow larger, the need for neutrons tends to increase. Heavier nuclei often require more neutrons than protons, because the proton repulsion becomes more severe, and additional neutrons help supply binding without worsening that repulsion. So the neutron is not merely tolerated in the nucleus, it becomes increasingly necessary. The larger and more ambitious the nucleus, the more it relies on neutrons to keep the enterprise viable. Home, then, begins with force balance. The neutron belongs in the nucleus because the nucleus wants what the neutron offers. But there is more to it than force alone. The quantum structure of nuclei matters as well. Nucleons occupy discrete energy levels in a way that is loosely analogous to how electrons occupy shells in atoms, though the details are of course different and far more tangled in practice. Certain numbers of protons or neutrons produce especially stable configurations. These are sometimes called magic numbers, and they reflect closed shells in nuclear structure. A neutron inside such a configuration can be part of an arrangement that is particularly favourable. In those circumstances, turning that neutron into a proton is not just a simple swap. It may disrupt a highly organised pattern and make the nucleus less comfortable overall. This is one reason the fate of a neutron depends so much on which nucleus it is in. There is no universal answer that says a neutron inside matter always survives or always decays. Some nuclei are stable, some are radioactive, some can undergo transformations in which a neutron becomes a proton, or a proton becomes a neutron. The deciding factor is the total energy and structure of the entire nucleus. The nucleus is a collective negotiation. Each neutron matters, but none is being judged in splendid isolation. That idea can feel unfamiliar because human intuition likes objects that carry their destiny around inside themselves. We imagine a thing has a built-in nature and that nature alone determines what happens next. Physics keeps reminding us that context matters. A neutron is one thing when free and another sort of participant when bound. The weak interaction still permits the possibility of transformation, but whether that transformation actually happens depends on whether the nucleus as a whole would end up in a lower energy state afterward. In many stable nuclei it would not, so the neutron stays as it is. You can think of it almost like language. A word on its own may have one role, but in a sentence it can do something different because the grammar of the whole line now matters. The neutron alone is a particle with a path toward decay. The neutron inside a nucleus is a particle whose role is constrained by the grammar of the full nuclear sentence. Change one word, and the whole sentence may become clumsy or invalid. So the original word remains, not because it forgot how to change, but because the larger structure prefers it where it is. There is also the matter of binding energy, which is one of the quiet master concepts behind all of this. When protons and neutrons bind together into a nucleus, the total energy of the resulting system is lower than the sum of the separated particles. That difference is the binding energy. It represents the energy released when the nucleus forms and the energy that would have to be supplied to break it apart again. A bound nucleus is, in that sense, energetically comfortable compared with its separated ingredients. The neutron inside such a nucleus is part of that comfort. Its presence contributes to a lower energy whole. Remove it or change it into something else, and you may lose some of that advantage. This is exactly why a free neutron and a bound neutron live such different lives. A free neutron is judged only against the alternative of becoming a proton plus the other products of decay. The proton is slightly lighter, so that option is available and favourable. A bound neutron is not judged alone. Its possible decay must be weighed against the resulting nucleus. If the new nucleus would be heavier in total or otherwise less favourable, then the decay does not proceed. The neutron remains, and it can remain for astonishingly long times. It is not being protected by a magical shield. It is being stabilised by the economy of the whole nucleus. The beauty of this is that it makes the nucleus feel less like a prison and more like a fit. The neutron does not merely survive there by force, it belongs there in the energetic sense. It finds a place where its existence supports the entire arrangement, and where that arrangement supports its continued identity. That is about as close as physics gets to home without becoming embarrassingly sentimental. And the fit is not only energetic, it is structural. Neutrons and protons together form nucleons, and these nucleons interact in ways that reflect both their closeness and their differences. The strong interaction between them is short-ranged and powerful. At very short distances it binds. At still shorter distances there is also a kind of repulsive core that prevents everything from collapsing into a single impossible lump. So the nucleus is a balanced system, neither flying apart nor crushing into featureless sameness. Neutrons play a central role in that balance. They help create enough attraction to hold nuclei together, while preserving the subtle spacing and organization required for a real nucleus to exist. This becomes especially important once you move beyond the lightest elements. Hydrogen can manage with just one proton. The most common helium nucleus contains 2 protons and 2 neutrons, already showing the pattern of partnership. Carbon, oxygen, silicon, calcium, iron, all the familiar elements that make planets, oceans, bones and stars rely on nuclei, in which neutrons are not optional decoration but structural necessity. They are part of what allows enough protons to coexist in one compact nucleus without the whole thing flying apart from electrical repulsion. In that sense, every ordinary object around you is a record of neutrons finding a way to stay at home inside nuclei. This also explains why isotopes are such a revealing idea. An isotope is a version of an element with the same number of protons but a different number of neutrons. The chemistry stays mostly similar because chemistry cares mainly about electrons and thus about proton number, but the nuclear character can change dramatically. Add or subtract neutrons and you can move from stable to unstable, from common to rare, from harmless to radioactive. That tells you how sensitive the nucleus is to neutron arrangement. The neutron is not just permitted there. It is part of the fine-tuning of the system. Take carbon as a simple example in spirit, though not in symbols. One common form of carbon is stably content with 6 protons and 6 neutrons. Add 2 more neutrons, and you get another stable isotope. Add still more or remove some and the balance changes. Some isotopes live a long time, others do not. The proton count keeps the atom carbon. The neutron count decides what sort of nuclear life that carbon leads. So when a neutron enters a nucleus, it is not just taking up space, it is changing the stability landscape. There is something else that makes the nucleus feel like home for the neutron, and that is companionship by similarity. The neutron and proton are so closely related that the nucleus is naturally built to host both. They are almost interchangeable from the point of view of the strong interaction, though not exactly. This is why nuclear matter can be made of both species in such intimate proximity. The nucleus is not built for protons alone, or neutrons alone in the ordinary sense. It is built from nucleons, with the neutron and proton as paired participants. Their differences matter, but their kinship matters too. The neutron is not an outsider there. It is one of the 2 main forms the nucleus expects. This is a good moment to notice how different this is from the electron-s relationship to the atom. Electrons live outside the nucleus in distributed quantum states. They define chemistry, bonding, light emission, conductivity, and the whole lively business of molecular life. Neutrons do not inhabit that outer region. Their place is deep in the centre with the protons, in the dense tiny heart of the atom. They are creatures of the nucleus, not of the wider atomic cloud. In a very literal sense, that is where their natural role exists. To ask why the nucleus feels like home to the neutron is a bit like asking why the sea feels like home to a fish rather than a bookshelf. It is the environment in which its defining usefulness actually operates. Still, the metaphor only goes so far because unlike a fish, the neutron is not choosing. It is not aware. It is not relieved to be indoors. The reason the home metaphor works at all is that the neutron's stability is conditional on the environment. In the nucleus, the overall system can prefer it as a neutron. Outside, the system made of that neutron alone does not. Physics turns home into a question of favoured arrangement. There are even cases where the nucleus can make the opposite choice. Some nuclei contain too many neutrons relative to protons. In those cases, the balance may improve if one of the neutrons changes into a proton. Then a radioactive decay can occur. The nucleus adjusts itself, moving toward a more favourable ratio. So even home has standards. The neutron is welcome when it helps the arrangement. If there are too many, the nucleus may gradually transform some of them. That does not weaken the home analogy. If anything, it sharpens it. A stable nucleus is not a random shelter. It is a carefully balanced household with quite strict accounting. This is why nuclear charts are so rich and why physicists speak of valleys of stability. Some combinations of protons and neutrons produce durable nuclei. Others sit off to the side, too proton-rich or too neutron-rich, and they decay toward more stable forms. The neutron is central to this entire geography. It is one of the main coordinates of nuclear existence. A nucleus finds its home when it reaches a combination in which the numbers and arrangement of neutrons and protons work together rather than against one another. There is also a practical consequence of the neutron feeling at home in nuclei. It means the visible world can store enormous numbers of neutrons safely and quietly within matter. Your body contains them. So does the Earth. So do the walls, the oceans, the moon, the air in various nuclei, the iron in the core of planets, the calcium in old stone buildings, the silicon in sand. Most of those neutrons are not free to decay because they are part of nuclei whose total structure favours keeping them there. We live inside a universe that has found a way to house these otherwise unstable particles in long-term arrangements. Matter, in that sense, is one of the universe's great storage systems for neutrons. Without that possibility, the world would be startlingly impoverished. Only the lightest nuclei would be common. Heavy elements would be much harder or impossible to maintain. Chemistry would shrink. Planets would change. Biology would never have the raw materials it now takes for granted. The fact that the neutron finds stability in nuclei is not a narrow technical detail. It is one of the reasons there is a rich material universe at all. What makes this especially satisfying is that it turns instability into usefulness. The free neutron cannot last forever, but that very same particle, when placed in the right nuclear context, becomes one of the main supports of durable matter. The neutron is not a failed proton. It is not an almost stable object that nature reluctantly tolerates. It is a particle whose proper role only becomes clear inside collective systems. Alone, it has one fate. In company, it helps build the world. So when we say the atomic nucleus feels like home, we mean that the nucleus offers the neutron an energetic fit, a structural role, a quantum environment, and a set of interactions in which staying a neutron often becomes the most favourable option. It can contribute binding, soften proton repulsion, occupy allowed nuclear states, and stabilise the whole. The home is not gentle in any everyday sense. The nucleus is still an extraordinarily dense place, with immense forces acting over tiny distances. But it is exactly the sort of place where the neutron makes sense. It is where its presence is not an accident but an advantage. And that sets up the contrast all the more sharply, because once the neutron leaves that environment, once it becomes truly alone again, all the support of the nuclear household falls away. There is no larger system left to justify its extra mass. No proton crowd to help organise, no binding energy to shelter its identity. It is just the neutron by itself, with the weak interaction still available and a slightly lighter sibling waiting as the more favourable outcome. At that point, the loneliness is not poetic, it is physical. And that physical loneliness is where the neutron begins to reveal its most personal secret, if one may borrow that word for a particle that has absolutely no interest in secrets, privacy, or emotional development. Once a neutron is truly on its own, stripped of the nuclear setting that helped make its identity a good fit, it finds itself in a situation that the laws of nature do not regard as especially permanent. Nothing dramatic happens at once. It does not burst like a soap bubble. It does not instantly disassemble in protest. For a while it simply continues being a neutron, but it is living on borrowed time, and the amount borrowed is not very large by the standards of particle physics. Left free and unbound, a neutron survives only for a short while before changing into something else. That fact is one of the most revealing in all of basic physics, because it forces us to stop thinking of particles as little eternal beads and start thinking of them as allowed states that may or may not be the most stable option available. A free neutron is real. It can travel. It can be stored briefly. It can be measured. It can even be guided and used in experiments of extraordinary precision. But it is not the final resting place of its own ingredients. Nature has a slightly cheaper arrangement available, and given a little time, the neutron takes it. The most important word there is slightly. If the neutron were wildly unstable, the story would be simpler but less interesting. If it vanished almost instantly, it would feel more like a temporary flare than a genuine constituent of matter. But the neutron lasts long enough to make its instability subtle. It survives for minutes, not for a tiny fraction of a second. That means it is stable enough to matter, and unstable enough to be telling us something. It occupies a middle ground that turns out to be unusually rich. It is not one of those particles that flash into existence in high-energy collisions, and are gone before anyone can think clearly. Nor is it a completely permanent resident of the universe when isolated. It is a respectable but temporary guest. The reason it cannot survive for long comes back to the delicate balance we were just talking about. The neutron is slightly heavier than the proton. That difference is small, but it gives the neutron a way out. A free neutron can reduce the total energy of the situation by becoming a proton, provided the transformation also produces the other particles needed to keep the laws of nature satisfied. And that is exactly what happens. One of the neutron s-down quarks changes into an up quark through the weak interaction. The neutron then becomes a proton, and in the process an electron and an antineutrino are also produced. The products together carry away the right amounts of energy, momentum, and other conserved quantities. The universe, as ever, keeps the books balanced even while changing the furniture. It is worth pausing on the phrase weak interaction because it sounds a bit underwhelming, almost apologetic. One hears strong interaction and imagines muscular certainty. One hears weak interaction and imagines something that should perhaps lie down with a blanket and a cup of tea. In fact, the weak interaction is entirely respectable. It is called weak because compared with the strong interaction and the electromagnetic interaction, its effects are much less likely to show up in many ordinary circumstances. But it is the interaction responsible for certain kinds of radioactive decay and particle transformation, and without it a remarkable number of familiar processes in the universe would simply not occur. The lonely neutron cannot survive because the weak interaction gives it a path to become something more stable. That path is not fast in the way nuclear or strong interaction processes can be fast. The strong interaction acts with astonishing urgency at tiny scales. The weak interaction, by comparison, is leisurely. In particle terms, it takes its time. That is why the neutron does not decay immediately. The allowed transformation exists, but it is not an overwhelmingly rapid one. This is one of the reasons the neutron feels almost conflicted when free. It is not comfortable enough to last forever, but not uncomfortable enough to make a scene. It lingers, and then eventually gives in. If this sounds as though the neutron is choosing, let me quickly rescue us from that metaphor before it gets too ambitious. The neutron is not debating options over a kitchen table. There is no tiny internal voice saying, "Perhaps I should become a proton and simplify my life." What is really happening is that quantum processes assign probabilities to different outcomes, and over time a population of free neutrons will decay according to a characteristic pattern. Some go a little sooner, some a little later. But on average, the times fall into a very regular statistical law. That law is one of the great signatures of radioactive and unstable systems. Individual events cannot be predicted in detail, but the collective behaviour is astonishingly orderly. This can be a difficult idea for the mind to accept at first because it asks us to hold two things at once. On the one hand, any given neutron does not come with a little countdown clock we can read. We cannot point to one neutron and say with certainty that it will decay exactly then. On the other hand, if we prepare a large number of free neutrons, the overall rate at which they disappear follows a precise pattern. The uncertainty lives at the level of the individual event. The reliability lives at the level of the ensemble. Physics is very fond of this arrangement. It is one of the ways nature manages to be both unpredictable and obedient at the same time. So why is the proton the favoured destination? The simplest answer is that it is lighter, and the weak interaction allows the necessary quark change. A neutron is made of one up quark and two down quarks. A proton is made of two up quarks and one down quark. Change one down quark into an up quark, and the identity changes accordingly. Because the proton sits slightly lower in mass, the final state is energetically allowed. The electron and antineutrino appear because the transformation must preserve the deeper rules governing charge and other quantum numbers. Nothing is improvised. The decay is lawful through and through. There is something rather elegant in that. The neutron does not fail because it is poorly built. It changes because the universe permits a lower energy arrangement with all the proper accounts settled. This is very different from the way ordinary objects break. A chair collapses because a leg snaps or a joint weakens. The neutron does not suffer wear and tear. It does not decay because it has been overused. It decays because the laws of nature allow a more stable state, and because the weak interaction provides the root. Its loneliness is not mechanical, it is energetic. That distinction becomes especially important when people first learn that the neutron is made of quarks. There can be a temptation to imagine that the quarks somehow come loose, drift apart, or rearrange themselves the way pieces of a machine might. But that is not how it works. The neutron remains a tightly bound hadron throughout its life as a neutron. Its quarks are confined. The strong interaction is still doing its job beautifully. What changes is the flavour of one quark through the weak interaction. The neutron is not falling to bits in the ordinary sense. It is transforming from one allowed hadronic state into another. This is why a free neutron can seem so oddly dignified. It is unstable, yes, but not chaotic. It continues as itself for a while. Then, through a process built deep into the structure of particle physics, it becomes a proton with a very orderly set of companions. One cannot really ask for a more civilized form of disappearing. And yet the consequences of that disappearance are large. If free neutrons lasted forever, the universe would behave differently on scales ranging from the subatomic to the cosmic. The early universe, for one thing, would have assembled matter in a different balance. Stars would not follow the same histories. Nuclear processes in laboratories and reactors would not work in the same way. The fact that the free neutron has a limited lifetime is not a quirky side note. It is part of the deep architecture that helps shape which elements formed and how matter evolved after the beginning of the universe. In the early cosmos, during the first few minutes after the hot beginning, protons and neutrons were present in a changing balance. As the universe expanded and cooled, free neutrons began to matter in a very practical sense, because they could either be incorporated into nuclei or decay away. The competition between those two possibilities helped determine how much helium and other light nuclei would form. That means the neutron's inability to survive alone for long is written into the chemistry of the cosmos. Every later structure built from those early ingredients carries a trace of that fact. Even something as ordinary as the abundance of hydrogen compared with helium is part of the neutron-s story. There is also an earthly side to this. Free neutrons are produced in reactors, in cosmic ray interactions, in particle experiments, and in various nuclear processes. But when they are slowed and isolated, they do not remain as a long-term free population. They either get captured by nuclei or they decay. A lonely neutron is always living in a world with limited options. Either it finds a nucleus that wants it, or it becomes a proton. There is no stable bachelor life available. That image may be a little unfair to bachelors, but the physics is solid enough. The neutron is one of those particles whose natural state is not defined solely by its internal structure, but by the company it keeps. In a nucleus, it can remain itself because it contributes to a favourable collective arrangement. Outside a nucleus, there is no such arrangement to justify the extra mass. This is why the loneliness matters. It is not loneliness as a feeling. It is loneliness as the absence of the very environment that made the neutron make sense over long times. We should also be careful not to overstate the melancholy. The neutron is not a tragic particle. It is a useful one. Its temporary freedom is extremely valuable in science. Because it carries no net electric charge, a free neutron can pass into materials and interact with nuclei and magnetic structures in ways that reveal information other probes might miss. Entire experimental programs are built around cold neutrons, ultra-cold neutrons, neutron scattering, neutron imaging, and precision measurements of neutron properties. So even the neutron-S brief solo career has been remarkably productive. One could almost say that, given only a short time to live, it has chosen academia. Its finite lifetime has also provided a long-running challenge for experimental physicists, because measuring that lifetime precisely turns out to be harder than one might guess. One can count how many neutrons remain after storing them for a while, or one can count the products of their decay, and these approaches have historically not agreed perfectly. That discrepancy has been a persistent little puzzle in modern physics. I mention it not to drag us into technical weeds, but because it reminds us that even a seemingly simple question such as how long does a free neutron live can become a subtle test of both experiment and theory. The lonely neutron, despite being a very old acquaintance in physics, is still capable of making researchers frown thoughtfully into expensive apparatus. That, in its own way, is part of the charm. The neutron is not obscure because it is too exotic to matter. It is familiar enough to be central and strange enough to resist complete simplification. It is one of the basic constituents of nuclei, and yet when freed it becomes an unstable system whose lifetime must be measured with care. It is a particle you can explain to a schoolchild in one sentence, and then spend a career studying with world-class instruments. There are not many better examples of how science works. The closer you get, the more the plain things become deep. There is another subtle point hidden in the phrase "cannot survive for long." The neutron does survive for a while. That means there is no contradiction in producing free neutrons and using them before they decay. In reactors, for instance, free neutrons can travel and trigger fission long before their natural decay would catch up with them. In neutron beams, they can be guided into experiments. In astrophysical environments, they can participate in nucleosynthesis. So the neutron-S loneliness is significant, but not instantly fatal. It exists in a regime where time matters, but does not dominate every moment. That gives the particle a peculiar practical importance. It is unstable enough to transform and stable enough to be useful. This middle character is one reason the free neutron feels almost human in the stories people tell about it, though we should resist the urge to become too sentimental about a hadron. It is neither eternal nor ephemeral. It is not one of the universe's S-fixed foundations like the electron seems to be, nor is it one of the fleeting resonances that appear and disappear almost before they can be named. It occupies a kind of respectable in-between. It can join nuclei and last for ages. It can leave them and continue for minutes. It can alter matter, reveal structure, and then quietly become something else. If particles had biographies, the neutron would have one of the more interesting ones. And of course, the real meaning of its inability to survive alone is not just that it vanishes, but that it tells us something about what stability really means. We often speak as though a particle either is stable or is not. The neutron insists that the better question is stable under what conditions. Free, it is unstable. Bound in many nuclei, it is effectively stable. Bound in other nuclei, it may eventually transform. The particle itself does not carry a single eternal label independent of circumstance. Its fate depends on the energetic landscape it inhabits. That is a profound lesson wrapped in a very small object. The free neutron also gives us a direct glimpse of the weak interaction at work in ordinary matter we tend to associate the weak interaction with distant stars, radioactive decay, or the deeper formalism of particle theory. But here it is, quietly changing one quark inside a familiar nuclear constituent and thereby reshaping the identity of the particle. The weak interaction does not usually dominate the visible structure of things the way electromagnetism does, and it does not hold matter together the way the strong interaction does. Yet, it governs change in a very deep sense. The neutron can endure because of the strong interaction, but it can transform because of the weak one. The lonely neutron is where those truths meet. It is almost impossible to think about this for long without noticing how much of nature depends on these competing influences being balanced just so. If the weak interaction acted differently, the neutron lifetime would change. If the neutron-proton mass difference changed, the decay might become slower, faster, or impossible. If the early universe had followed a different timing, the abundance of light elements would differ. We are used to the ordinary world, so we rarely stop to notice how many tiny balances had to line up for that ordinary world to emerge. The lonely neutron is one of the clearest windows into that hidden tuning, and still, perhaps the most intuitive version of the story is the simplest one. A neutron outside the nucleus no longer has the support of a larger structure. It is left with its own internal makeup and the laws that govern possible transformations. Since a proton is a slightly lighter close relative, and since the weak interaction permits the needed quark change, the neutron cannot remain alone forever. It is not that isolation damages it, it is that isolation removes the reasons for it to stay as it is. That is why nuclear matter feels so different from free space for a neutron. In the nucleus, it belongs to a cooperative arrangement. Alone, it is just a particle carrying a little extra mass and a path toward becoming something else. It continues bravely enough for a while, then yields, and once you follow that process even a little way, the next thing you naturally want to watch is the transformation itself, because the neutron does not simply disappear. It leaves behind a very particular set of products, and in that graceful little act of self-replacement, it reveals even more about how the universe keeps its accounts. What makes the decay of a neutron so satisfying to think about is that it is not violent in the way people often imagine particle change to be. The word decay can sound messy. It suggests rot, collapse, damage, something fraying at the edges until it gives way. But a neutron does not go soft or crack or wear down with age. It does not grow tired of being itself. It changes in a way that is precise, lawful, and surprisingly restrained. That is why gentle collapse is not a bad phrase for it. A free neutron does not explode into chaos. It quietly becomes something slightly simpler and slightly more stable, and in doing so it gives us one of the clearest demonstrations of how the weak interaction works in the real world. The first thing to hold on to is that the neutron does not stop being a neutron, because the strong interaction has failed to keep its quarks together. That would be the wrong picture entirely. The neutron remains a tightly bound hadron right up until the moment of decay. Its quarks are still confined, its internal structure is still very much in place. The strong interaction is not losing its grip. What changes is something more subtle. One of the down quarks inside the neutron changes into an up quark through the weak interaction. That single change is enough to alter the identity of the whole particle. The neutron, with one up quark and two down quarks, becomes a proton, with two up quarks and one down quark. That transformation alone would already be remarkable, because it means that the identity of a particle is not some sacred label fixed forever, no matter what happens inside it. Change the right ingredient in the right way, and the whole object becomes something else. But the process has to satisfy a number of deeper rules as well. Charge must still balance, energy must still balance, momentum must still balance. Other quantum properties must also come out properly. That is why the neutron does not simply become a proton and call it a day. An electron is emitted, and so is an antineutrino. Together, the proton, electron, and antineutrino make the accounting work. This is the part that often feels almost magical when one first hears it. a neutron becomes a proton and also gives off an electron. Where did the electron come from? Was it hiding inside the neutron all along? The answer is no. It was not sitting in there waiting behind the curtains. The electron is created in the decay process itself. When the down quark changes into an up quark, the weak interaction produces the additional particles needed to preserve the deeper conservation laws. In older nuclear pictures, people sometimes imagined electrons living inside nuclei as permanent residents. Modern particle physics tells a much cleaner story. The electron in neutron decay is not pre-packed inside the neutron in the old-fashioned sense. It appears as part of the transformation. That matters because it changes how we think about matter itself. The neutron is not a little container full of pre-existing future products. It is a quantum state that can evolve into another allowed state. The products emerge according to the rules of the interaction, not because they were waiting in literal miniature form inside the original particle like props in a magician-esque sleeve. The decay is not an unpacking, it is a conversion, and conversion is really the right word here. The neutron does not get smashed from the outside in ordinary free decay. It does not need a collision to force the issue. Left on its own, it simply has an available route to a lower energy arrangement, and the weak interaction makes that route possible. The process is called beta decay, though what matters more than the name is the idea behind it. A constituent quark changes flavour. The particle changes identity. Additional particles are emitted to keep the books balanced. The result is a proton where once there was a neutron. If you slow the story down almost frame by frame, as much as one can without making it unreadable, the sequence looks like this. A free neutron exists as a bound state of quarks and gluons. Because it is slightly heavier than the proton, the overall system contains enough excess mass energy to permit a change. Through the weak interaction, one down quark turns into an up quark. In that same act, a carrier of the weak force is involved, and that then leads to the appearance of an electron and an antineutrino. Once the quark content has changed, the original hadron is no longer a neutron, it is a proton. The electron and antineutrino fly away, carrying off energy and momentum. What people often find surprising is that the electron does not always come out with the same energy. If neutron decay were a simple two-body process, you might expect the final products to emerge with fixed, well-defined shares of energy. But the decay produces three final particles, and that means the available energy can be divided among them in different ways from one event to another. The proton gets a little, the electron gets some, the antineutrino gets some, and the exact distribution can vary. This was historically a very important clue. Early measurements of beta decay showed that the emitted electrons did not all have a single neat energy value. Instead, there was a spread. That was deeply puzzling until the neutrino idea entered the picture. This is one of those lovely moments where a tiny neutral particle rescues the logic of the universe. If electrons from beta decay came out with varying energies, then either energy conservation was failing in radioactive processes, which would have been a very dramatic and unwelcome development, or there was another unseen particle carrying away the missing share. Wolfgang Pauli proposed such a particle in the early 1930s, rather apologetically at first, because inventing an invisible particle to save conservation laws can sound a little desperate if one is not careful. But it turned out to be exactly the right move. The neutrino, and in neutron decay specifically the antineutrino, explained the missing energy and momentum beautifully. So the gentle collapse of the neutron ended up teaching physics two things at once. It showed that particles can transform through the weak interaction, and it helped reveal the existence of one of the strangest and most elusive particles in all of nature. The antineutrino is extraordinarily difficult to detect. It carries no electric charge, has an incredibly small mass, and interacts only very weakly with matter. That means when a neutron decays, one of the products usually escapes with almost ghost-like indifference to the surrounding world. The proton may stay nearby if the neutron was in an experimental trap. The electron can be detected more readily. The antineutrino is usually gone before anyone can make much of a fuss. There is a certain irony in that. The neutron itself once seemed hidden because it carried no charge. Then in its decay it reveals another neutral elusive product that is even harder to catch. Particle physics has a recurring habit of solving one quiet mystery by introducing another quieter one. Still, at the core of the process is a very concrete fact. One quark changes flavour. That deserves emphasis because it is such a fundamental kind of change. The strong interaction keeps quarks bound into hadrons, but it does not change one flavour of quark into another. The weak interaction does. It is the part of nature that allows matter to transmute in this deeper sense. A down quark can become an up quark. An up quark under other conditions can become something else. Without the weak interaction, the world would be far more static. Radioactive transformations would not proceed the way they do. The sun would not shine through the chain of processes it actually uses. The neutron would not have its quiet route into protonhood. This is one reason the weak interaction deserves more respect than its name suggests. It is not weak in importance. It is weak in comparative strength and in the probability of certain processes, but it governs some of the most essential changes in nature. Whenever an unstable nucleus adjusts its composition, by converting a neutron into a proton or vice versa, the weak interaction is involved. Whenever beta decay occurs, it is there. Whenever the balance of particles in stars shifts through these kinds of processes, it is there as well. The neutron is one of the clearest places where that abstract statement becomes real and personal. There is also something very revealing in the timing of neutron decay. A free neutron does not transform instantly, which tells you that the available process is permitted but not overwhelmingly favoured in the rapid way strong interaction decays can be. The weak interaction gives the neutron a route, but not an urgent shove. That is why neutrons can be stored for a while in carefully designed experiments. It is why neutron beams can be used in laboratories before the particles decay away. It is why the process feels almost patient. The neutron is unstable, but not frantic. It changes on a timescale slow enough for humans to take an interest and build apparatus around it, which is rather generous of it, really. At the same time, the decay is not deterministic for any one individual neutron. We cannot look at a specific free neutron and declare exactly when it will decay. The process is probabilistic. Each neutron has a certain chance per unit time to decay, and over a population the numbers follow a clean statistical law. That means one neutron might decay a bit earlier, another a bit later, but the ensemble behaviour remains regular. This is not a flaw in our knowledge. It is the kind of rule quantum physics gives us. The world at that level does not always hand out exact schedules to individual events. It hands out probabilities that become beautifully exact in the aggregate. That statistical character was one of the great conceptual adjustments of modern physics. People had to get used to the idea that the best possible description of certain processes was not a hidden timetable, but a probability. The neutron fits into that lesson perfectly. Its decay is not lawless because the timing of one event is uncertain. It is lawful because the distribution of many events is precise, and because the underlying interaction rules are exact. The universe is not being vague, it is being quantum. Another aspect of the process that deserves a calm look is the role of energy. We keep saying that the neutron is slightly heavier than the proton, and that this makes the decay possible. That statement can sound dry until one remembers what mass means in this context. Because mass and energy are related, a heavier particle can transform into a lighter one if the difference appears as energy carried by the products. In neutron decay, that is exactly what happens. The proton is lighter. The remaining difference is shared among the motion of the proton, the energy of the electron, and the energy of the antineutrino. Nothing is wasted. Nothing simply disappears. The initial and final totals remain in balance. This kind of bookkeeping is one of the reasons particle physics, for all its strangeness, ends up feeling oddly reassuring. The entities involved may be bizarre, the processes may be invisible, the language may at times sound as though it was assembled by a committee of mathematicians who had misplaced the ordinary nouns, Yet underneath it all, the logic is extremely strict. Charge is conserved, energy is conserved, momentum is conserved. The neutron is allowed to decay not because the laws are loose, but because the laws permit a very specific transformation that satisfies all of them at once, and it satisfies them with a certain elegance. The charge of the original neutron is 0. In the final state, the proton carries positive charge and the electron carries negative charge, which together sum to 0. The antineutrino carries no electric charge. The quark flavor change explains the identity shift. The available energy explains why the process can happen at all. The three-body final state explains why the electron energies form a spectrum rather than a single fixed value. Each detail that once looked puzzling turns out to be part of a coherent whole. Historically, this made neutron decay a very rich testing ground for theory. It was not just another radioactive oddity to be catalogued and shelved. It became a way to probe the weak interaction, to test conservation laws, to study parity and other subtle features of particle behaviour, and to examine how quark-level processes show themselves in ordinary matter. The neutron is familiar enough to be handled and strange enough to be fundamental. That is a rare combination. It gives experimenters something tangible to work with, and theorists something deep to explain. Even today, neutron decay remains an active area of precision study. Physicists measure the neutron lifetime, the angular patterns of the emitted particles, the details of the energy distributions, and the correlations among the decay products, all because these measurements test the structure of the weak interaction and may even hint at physics beyond the current standard framework if something ever refuses to line up. The decay is gentle, but it is not trivial. It is a tiny event with large implications. There is also a more intuitive human way to see the process. The free neutron is carrying just a little too much mass to remain the lowest available form of itself. It is like a system with a small extra burden and a lawful path towards setting that burden down. The proton is what remains once the shift has happened. The electron and antineutrino are the necessary outgoing messengers of the transformation. The collapse is gentle because nothing is smashed apart by force. The neutron simply rearranges into a more comfortable outcome, allowed by the rules it lives under. That is why one should resist the temptation to picture decay as destruction. In ordinary language, destruction sounds like a thing ending in disorder. Neutron decay is not disorder. It is reorganization. It is a move from one stable pattern of quarks and fields to another, with precisely the right additional particles produced along the way. The original neutron ceases to exist as a neutron, yes, but the matter and energy do not vanish into confusion. They are redistributed into a proton, an electron, and an antineutrino with impeccable discipline. The proton that emerges is especially interesting because it is the particle that ordinary hydrogen is built around. So every time a free neutron decays, it quietly produces one of the most durable and common building blocks in the universe. There is something almost domestic about that. The lonely neutron does not end in ruins. It ends by contributing to the proton-rich world we already know so well. In a sense, free neutron decay is one of the ways the universe nudges matter back toward its more durable everyday form. And yet the neutron never becomes unimportant just because it can decay. Quite the opposite. The possibility of decay is part of what makes neutrons so significant in cosmology, astrophysics, and nuclear processes. In the early universe, free neutron decay helped shape the balance of light elements. In radioactive nuclei, neutron to proton conversion helps move unstable isotopes toward more favorable forms. In stars and explosions, related weak processes influence how matter evolves under extreme conditions. The decay is gentle in mechanism, but its consequences spread very far. That is one of the great pleasures of physics. A small event can matter on huge scales without becoming any less precise. A single neutron decay in a lab is tiny, local, and quiet. The same process, repeated across the early universe or inside vast astrophysical environments, becomes part of the reason there are stars, elements, and planets with the compositions they have. The local event and the cosmic consequence are the same story viewed at different distances, so when a neutron decays, what we are really watching is a quiet act of adjustment. A down quark changes into an up quark. The hadron becomes a proton, an electron and an antineutrino are emitted. Energy and momentum are shared. Charge remains balanced. The strong interaction continues to bind the hadronic state that remains. The weak interaction has done its work and stepped back. Nothing theatrical is required. The laws are enough. And because the laws are enough, the neutron becomes far more than a neutral particle in the nucleus. It becomes a kind of hinge between stability and change. In one setting, it helps hold matter together. In another, it transforms and helps matter move toward new forms. That is why following its decay matters so much. It is not only a story about one particle failing to survive alone, it is a story about how the universe reshapes itself, quietly and lawfully, one small conversion at a time. Once you see the decay that way, the neutron stops looking like an isolated curiosity and starts looking like a participant in much larger stories. Its gentle collapse does not end the tale. It opens outward into questions about why free neutrons matter in the first place, how their short lives influence the early universe, how their capture and release help build heavier elements, and why this apparently modest particle turns out to sit close to the center of both ordinary matter and some of the most extreme environments in the cosmos. And that is really where the neutron stops being merely an interesting case of particle decay and becomes something much larger. Because once you understand that a free neutron can live for a while, interact with other matter, and then either be captured or decay, you begin to see that this modest neutral particle has influence far beyond its size. It is involved in the earliest minutes of the universe, in the life cycles of stars, in the making of elements, in the stability of atomic nuclei, and in the practical tools humans use to study matter itself. The neutron matters not because it is loud, but because it sits at several important junctions at once. It is one of those pieces of physics that connects the very small to the very large with very little fuss. A useful way to begin is with the early universe, because that is where neutrons first had a chance to shape the broad chemical character of everything that followed. In the beginning, when the universe was far hotter and denser than anything we can comfortably imagine, protons and neutrons were not tucked safely into ordinary atoms. They were part of a hot mixture of particles interacting rapidly. At those immense temperatures, the distinction between what would later remain common and what would later decay away was not yet settled. Protons and neutrons could be converted into one another through weak interaction processes, and the balance between them shifted as the universe expanded and cooled. This matters because the neutron is slightly heavier than the proton. In the hottest, earliest moments, that difference did not dominate in the same quiet way it does later, because the whole environment was full of enough energy to keep many reactions going. But as the universe cooled, it became harder to keep converting protons into neutrons, while neutrons could still turn into protons or simply decay if left free for too long. That meant the cosmic supply of neutrons began to thin. They were living under a deadline. Either they would be captured into nuclei soon enough, or many of them would be lost to decay. And that deadline helped determine one of the most basic features of the universe we live in now, which is the abundance of hydrogen and helium. Once the universe cooled enough for light nuclei to form and survive without being immediately broken apart again, protons and neutrons began assembling into the first stable combinations. The easiest important destination for neutrons was helium. A helium nucleus contains 2 protons and 2 neutrons, which makes it tightly bound and very stable. So many of the neutrons that had not yet decayed were quickly locked into helium, while the remaining protons largely stayed as hydrogen nuclei. The result was a universe dominated by hydrogen, with a substantial fraction of helium and only trace amounts of a few, slightly heavier light elements. That is a remarkable thing to owe in part to the short life of the free neutron. If neutrons had lived much longer, The early balance might have shifted toward more helium, and perhaps more of some other light nuclei. If they had lived much less long, fewer would have survived to be captured, and the universe would have contained less helium. So the familiar fact that stars are mostly hydrogen, with a great deal of helium, is not just a random starting condition. It carries the imprint of neutron physics. Starlight, in a very direct sense, begins with how long lonely neutrons could hold on in the early cosmos before nuclei gave them somewhere to stay. Once stars formed, neutrons continued to matter in a different but equally important way. Stars shine because nuclei are transformed in their hot, dense interiors. In ordinary stars like the Sun, the main business is the conversion of hydrogen into helium, which releases energy because helium is more tightly bound. But even in that relatively gentle stellar work, weak interaction processes are essential. The proton-rich world we inherited from the early universe has to be coaxed into new forms, and neutron-related changes are part of the story. The strong interaction binds nuclei once the right ingredients are available, but the weak interaction often has to change the identity of particles to make certain steps possible. So although neutrons are not always sitting in the spotlight of every stellar reaction, their kind of transformation is woven into the machinery of how stars actually operate. There is also the question of what stars eventually make. Hydrogen and helium are not enough to build rocky planets, living tissue, oceans, metals, and all the familiar matter around us. For that, the universe needs heavier elements: carbon, oxygen, silicon, calcium, iron, and beyond. Those elements are forged in stars and in the violent events associated with stellar death. Neutrons are deeply involved in this process because they are unusually good at entering nuclei. A proton approaching a nucleus has to fight electrical repulsion. A neutron does not. That gives neutrons a special role in building heavier nuclei step by step through neutron capture. This is one of the reasons neutrons matter so much in element formation. A nucleus can absorb a neutron more readily than it can absorb a proton in many circumstances. Once the neutron is inside, the nucleus may remain stable, or may later undergo a transformation in which one of its neutrons turns into a proton. That changes the element itself because the proton number has increased. In this way, neutrons act as quiet couriers of growth. They slip into nuclei without electrical drama, and then, through later nuclear changes, they help move matter upward through the periodic table. A great many of the heavy elements in the universe were built in exactly this general way, not all at once, and not under one single set of conditions, but through neutron capture followed by radioactive adjustments. In some stellar environments, neutron captures happen slowly enough that unstable nuclei often have time to decay before capturing yet another neutron. In other, much more violent environments, neutrons are so abundant that nuclei can capture them in rapid succession before decay catches up. Those two broad styles of element making produce many of the heavy nuclei that later become part of planets, rocks, and living organisms. Gold, iodine, barium, uranium, and many others owe their existence to neutron-rich processes in stars or stellar explosions. That means the neutron is not just helping matter hold together, it is helping matter become more diverse. This is a very striking contrast with the older textbook image of the neutron as the quiet, neutral filler in the nucleus. Quiet, perhaps, but not filler. The neutron is one of the main routes by which the periodic table acquires its upper floors. Without neutron capture, the universe would have a much poorer chemical vocabulary. We would have light elements and only a very limited path beyond them. Instead, thanks to neutron-rich processes operating over cosmic history, matter becomes capable of astonishing variety. The calcium in bones, the iron in blood, the iodine used in biology, the rare metals in technology, the uranium in the earth, all belong to a universe where neutrons could be captured, held, and converted as needed. There is something satisfying in the way the neutron achieves this. It is not through brute charge or obvious force. It is through access. The neutron can enter where a proton is turned back. It can be added without immediately increasing the electrical burden of the nucleus. It gives the nucleus room to grow before the weak interaction later adjusts the proton count when that becomes favourable. The neutron, in other words, helps nature build complicated nuclei in stages, rather than demanding all the difficulty at once. Closer to home, the neutron matters not just in distant stars, but in the quiet durability of the matter around us. Every stable, heavy nucleus in ordinary material depends on neutrons helping offset proton repulsion. Without them, most of the elements that make up rocks, metals, and living bodies could not maintain their nuclei. Carbon would not be the same story. Oxygen would not be the same story. Iron would not be the same story. The neutron is part of why matter can be rich, layered, and varied rather than mostly limited to the very lightest nuclei. That means the neutron matters both at the beginning of matter and in its mature forms. It helped determine what the early universe could save from decay. It helps stars and explosions manufacture heavier nuclei. It helps stable nuclei remain stable in the everyday world. It participates in radioactive change where isotopes adjust toward better balance. It is one of the reasons matter can both last and evolve. Few particles get to be that broadly useful, and then there is the practical scientific importance of free neutrons, which is almost a second career entirely. Because neutrons have no net electric charge, they can be used to probe matter in ways that charged particles cannot. When physicists, chemists, and material scientists want to learn how atoms are arranged in a solid, how magnetic order is structured, how molecules move, or how a material changes under stress or temperature, neutron scattering can be an extraordinarily powerful tool. A neutron beam sent through a material will interact with nuclei and with magnetic moments, and by studying the scattered neutrons, researchers can infer details of the material S internal structure. This is one of those places where the neutron's neutrality becomes less a mystery and more a working advantage. Charged probes interact strongly with electrons and can be deflected or screened in ways that complicate the picture. Neutrons often pass more directly into the body of the material and sample features that other probes miss or blur. They're especially useful for locating light elements, studying magnetism, and examining motions inside complex materials. So the neutron not only helps build matter in the universe, it also helps us understand matter here on Earth. There is a quiet elegance in that. The same particle whose early cosmic lifetime helped shape elemental abundances can later be produced in human laboratories and used to study alloys, superconductors, proteins, crystals, batteries, and magnetic systems. The neutron crosses scales with almost absurd ease. It helps determine the composition of stars and then assists in analysing the internal structure of the material in a machine part or a biological sample. That range of usefulness is very rare. The neutron also matters in nuclear technology more directly. In a reactor, free neutrons play a central role because they can enter heavy nuclei and trigger fission. When certain large nuclei absorb a neutron, they become unstable enough to split into smaller nuclei, releasing energy and additional neutrons. Those additional neutrons can then continue the process. This is what makes a chain reaction possible. Once again, the neutron is the key because it can approach nuclei without facing the same electrical barrier that would stop a proton. The entire practicality of controlled nuclear fission relies on this neutral access. That same property is one reason neutrons are involved in the creation of many radioisotopes used in medicine, research, and industry. Expose certain nuclei to neutrons and they can capture them, becoming new isotopes that may later decay in useful ways. This can produce materials for imaging, treatment, tracing chemical pathways, or industrial inspection. So the neutron is not merely a participant in grand cosmic stories. It has become part of ordinary human technology in ways that are quite concrete. Even outside reactors and laboratories, neutrons continue to matter because cosmic rays striking the atmosphere can produce free neutrons among other particles. These neutrons contribute to radiation backgrounds, to isotope production in the environment, and to certain subtle processes in the air and on the surface of the Earth. The world is not flooded with them in any way that dominates everyday life, but their presence is another reminder that neutron physics is not confined to sealed reactors and distant stars. It is one of the ongoing threads in the natural environment. Another reason neutrons matter is that they are closely tied to some of the best tests of fundamental physics. Because the neutron is neutral, long-lived enough to be studied carefully, and composed of quarks, it sits in a useful middle ground between nuclear physics and particle physics. Precision measurements of neutron decay, neutron electric properties, and neutron interactions can reveal whether our standard theories are fully right or whether some deeper correction is still waiting to be found. The neutron is simple enough to work with in principle and complicated enough to be interesting in detail. That makes it a favourite subject for experiments designed to push at the edges of known theory. In that sense, the neutron matters intellectually as much as materially. It is one of the places where different areas of physics meet. Cosmology cares about it because of the early universe. Astrophysics cares about it because of stars and element formation. Nuclear physics cares about it because of stability and reactions. Particle physics cares about its quark structure and weak decay. Materials science cares about neutron scattering. Engineering cares about reactor behaviour. Very few particles manage to be so socially successful across disciplines. And perhaps that is why the neutron is often underestimated by people meeting it for the first time. It does not advertise well. It sounds neutral, secondary, almost background. Yet in practice, it is one of the great organisers of matter. It helps determine what nuclei can exist, how stars make heavier elements, how the early universe set its chemical proportions, how reactors function, how certain isotopes are produced, and how we study matter in fine detail. If the proton gives the universe identity in the form of element number, the neutron gives it flexibility, depth, and range. There is also the matter of timing, which is often overlooked. Free neutrons live long enough to matter. That simple fact is crucial. If they vanished almost instantly, they would be far less useful in neutron capture processes, in reactors, and in experiments. If they lived forever, the balance of early element formation and many later nuclear processes would change profoundly. Their lifetime sits in a range that makes them both effective and temporary. They can travel, be captured, participate in reactions, and also decay when left alone. That makes them a kind of transitional currency in nuclear processes, always able to join, leave, or be transformed depending on the environment. This helps explain why neutrons so often appear at turning points. A nucleus absorbs a neutron and becomes a heavier isotope. An unstable isotope later changes because one neutron becomes a proton. A reactor chain continues because neutrons from one fission event trigger another. Heavy elements are built because nuclei catch neutrons in stellar interiors or explosive events. The early universe locks neutrons into helium before too many decay away. Again and again, the neutron is involved when matter changes state, changes composition, or gains new possibilities. It is not only a building block, it is a facilitator. And that returns us quite naturally to starlight. Stars are often spoken of as furnaces, and fairly enough, but a furnace is only a beginning. A star is also a sorting place for matter, a place where simple nuclei become more complex, where the balance between proton and neutron-rich arrangements determines what can form and where the pathways to heavier elements open or close depending on the available conditions. The light from stars reaches us because nuclear processes release energy. The material richness of the world reaches us because stars and stellar deaths built elements through pathways in which neutrons had extraordinary importance. So when you look at starlight, you're not just seeing energy, you're looking at part of the long story by which the universe made both illumination and substance. Neutrons helped write that story. There is something almost modest about the way they do it. The neutron does not dominate chemistry directly the way electrons do. It does not define the element the way protons do. It works a little more quietly than either. But it is the reason nuclei have enough room to become large and stable. The reason heavy element synthesis has efficient pathways, and the reason so many transformations can proceed without being stopped at the gate by electric repulsion. The neutron matters because it makes complexity possible at the nuclear level, and once you've noticed that, the next step is hard to avoid. Because if neutrons matter this much in ordinary nuclei, in stars, in reactors, and in element formation, then one naturally starts to wonder what happens when their role stops being moderate and becomes extreme. What happens when nuclei grow unusually heavy, when neutron capture becomes overwhelming, when matter is compressed so hard that neutrons are no longer just participants, but the main substance of the object itself. That is where the story moves from quiet usefulness to outright extremity, because there are environments in the universe where neutrons do not merely help matter along, they take over. And once neutrons start gathering in large numbers or in very energetic places, their importance becomes impossible to ignore. In ordinary matter, they are quiet residents of nuclei. In reactors, they become the moving pieces that keep a chain of events alive. In the making of elements, they become the easiest way for nuclei to grow beyond what protons alone could comfortably manage. And in one of the most extreme endings a star can have, they stop being supporting players altogether and become the main substance of an entire collapsed object. The same particle that cannot survive alone for very long can, under the right conditions, help run power stations, build gold and uranium, and support the remains of a dead star. That is a rather impressive range for something usually introduced as the neutral one in the middle. A good place to begin is with reactors, because reactors show the neutron in one of its clearest practical roles. A reactor is, at heart, a carefully managed environment in which certain heavy nuclei can split after absorbing a neutron. When one of those nuclei splits, it releases energy and also sends out additional neutrons. Those newly freed neutrons can then strike other heavy nuclei, which may split in turn. This creates a chain reaction. The crucial detail is that neutrons make the whole thing possible, because they can approach nuclei without facing the same electrical repulsion that a proton would face. A proton trying to enter a heavy positively charged nucleus is like someone trying to push through a door, while several large relatives on the other side are firmly leaning against it. A neutron, being neutral overall, does not get the same immediate refusal. That access is everything. It means neutrons can wander into nuclei, be captured, and trigger changes that charged particles would struggle to begin. In a reactor, this property is harnessed very carefully. The goal is not to let the process run away wildly, but to maintain a steady balance chain, in which, on average, each fission event leads to about enough future events to keep the reaction going at the desired rate. Too few neutrons successfully continue the chain, and the reaction fades. Too many, and the rate increases too much. So the reactor becomes, in a sense, a place where neutron life is managed like a very serious and highly regulated social event. Some neutrons are slowed down because slower neutrons are more effective at causing certain nuclei to split. Some are absorbed by control materials to keep the process in balance. Some escape. Some are captured in useful ways. The whole system depends on knowing that neutrons can travel through the core, enter nuclei, and keep the story moving. There is something satisfying about the fact that the same neutrality, which once made the neutron hard to discover, is exactly what makes it useful in reactors. The particle that did not announce itself easily to early experimenters turns out to be ideal for entering dense nuclear territory. It slips past the electrostatic objections and gets right to the point. That is one reason neutron behavior has to be studied so carefully in reactor design. The geometry of the fuel, the materials around it, the way neutrons scatter and slow down, the chance that they are captured instead of lost, all of it matters. A reactor is, among other things, a carefully arranged neutron environment. Neutrons also matter in reactors because they do not just trigger fission, they can produce new isotopes by capture. A nucleus that absorbs a neutron may become a heavier isotope and later decay into a different element. This can be useful or inconvenient depending on the context. In one setting, it's how certain valuable isotopes are made for medicine. industry and research. In another, it changes the long-term composition of reactor fuel and surrounding materials. The neutron is again acting as a quiet agent of change. It enters, it stays if allowed, and then the nucleus must decide what kind of life it now intends to lead. From there, it is a short step to the wider universe, because neutron capture is not something humanity invented. We merely learned to exploit it in specific machines. Nature has been using it for a very long time in stars and stellar explosions. In many environments, the easiest way for a nucleus to grow is not by adding protons one by one, since protons are electrically repelled by nuclei, but by adding neutrons. A neutron can be captured more readily. Once captured, the nucleus may remain stable for a while or later adjust by turning one of those extra neutrons into a proton. When that happens, the atomic number increases and the element changes. In this way, neutrons provide a practical route upward through the periodic table. That route is one of the great reasons the chemical world is so rich. Light nuclei alone are not enough to make planets, oceans, bones, blood, and all the subtler materials of geology and biology. The universe needed a way to build heavy nuclei. Neutron capture followed by radioactive adjustment is one of the main ways it did so. In quieter stellar settings, captures can happen slowly enough that unstable nuclei have time to decay between additions. In more violent conditions, captures can happen in rapid succession before decay catches up. Those different tempos produce different families of heavy elements. The details are intricate, but the broad idea is beautifully simple. Neutrons are the easy guests for a nucleus to admit, and once inside they can help transform the identity of the host. This means that many of the heavier elements around us are records of environments where neutrons were abundant enough and available enough to gather onto nuclei in large numbers. The gold in jewellery, the iodine used by living systems, the barium in old minerals, the uranium in deep rock, the rare metals in technology, none of these should be thought of as simply existing by default. They were built, and very often they were built by neutron-rich pathways that allowed nuclei to climb to forms they could never have reached through proton addition alone. The neutron is not only a stabilizer of nuclei that already exist, it is one of the main routes by which new kinds of nuclei come into being. There is something almost practical about how nature uses neutrons in this role. It does not insist on forcing protons past electrical barriers at every step. It takes the quieter path, add the neutral particle first, let the nucleus grow, then allow the weak interaction, when favourable, to convert some of that added neutron content into proton content. The element changes not because a proton barged in directly, but because a neutron entered politely and the nucleus later revised its internal balance. It is a very efficient strategy, and the periodic table is full of its results. Of course, not every gathering of neutrons is helpful in a gentle way. Too many neutrons in the wrong place can drive nuclei far from stability. Entire regions of nuclear existence are made of isotopes so neutron-rich that they can only survive briefly before adjusting. Yet even those short-lived nuclei matter, because they occupy the pathways through which the heaviest elements are assembled. The universe, in its more dramatic moments, does not always build matter through patient tidy steps. Sometimes it floods the situation with neutrons and lets nuclei race through strange temporary forms before settling back towards stability. The neutron is there in both moods of creation, the careful and the catastrophic. And that brings us naturally to the most extreme setting of all, because there are places in the cosmos where neutrons do not merely gather onto nuclei, but dominate matter on an almost unimaginable scale. These are neutron stars, the collapsed remnants left behind when certain massive stars end their lives. To understand why neutrons take over there, it helps to remember what a normal star is doing. Throughout most of its life, a star supports itself against gravity by the pressure generated from hot gas and nuclear reactions in its core. Gravity pulls inward, pressure pushes outward. As long as that balance holds, the star remains a star. But when a massive star exhausts the fuel that can sustain those reactions in its core, gravity begins to win. The core collapses. Matter is compressed to extraordinary densities. Under those conditions, electrons and protons are pushed into arrangements where it becomes energetically favourable for them to combine into neutrons. The star, or at least its collapsed core, becomes neutron-rich in the most literal way possible. What remains after the outer layers are blasted away in a supernova can be an object with more mass than the Sun packed into a sphere only about the size of a city. That object is supported not by ordinary gas pressure in the everyday sense, but by the quantum and nuclear behaviour of matter in a state where neutrons dominate. It is difficult to overstate how extreme that is. The neutron, which in ordinary matter sits modestly in nuclei, now becomes the main constituent of an entire stellar remnant. If you could somehow bring a spoonful of neutron star matter to Earth, which you absolutely should not attempt, even on a lively weekend, it would weigh an absurd amount. The density is so far beyond everyday experience that ordinary comparisons begin to sound unserious, but they remain the only tools language has. Matter there is packed to something approaching the density of atomic nuclei on a macroscopic scale. A neutron star is, in a very rough sense, a giant nucleus held together by gravity, though even that image is only the beginning of the story. Inside a neutron star, the exact structure is still an active area of research. The outer layers may contain nuclei and electrons in strange arrangements. Deeper down, neutrons dominate more strongly. Some of them may form superfluid states. The inner core may contain matter in conditions so extreme that physicists still debate its detailed composition. But whatever the finer truth turns out to be, the name neutron star is not decorative. Neutrons really are central to what such an object is. The particle that could not survive alone in free space now exists in overwhelming collective company under crushing gravity. One might say it finally found a neighbourhood with no shortage of support. There is a wonderful contrast there. A single free neutron lasts only a short while. A vast congregation of neutron-rich matter in a collapsed star can remain for immense spans of time. Context matters again, but now at the largest and most dramatic scale. The neutron-s instability and isolation does not prevent it from becoming part of one of the most durable and bizarre objects in the universe, when the surrounding conditions are extreme enough. What cannot survive alone can thrive in number under pressure. Neutron stars are also extraordinary because they reveal how deeply neutron physics connects to astrophysics. Their gravity is intense. Their magnetic fields can be enormous. Some spin rapidly and beam radiation through space like cosmic lighthouses, appearing to us as pulsars. Others collide with one another in spectacular mergers that send ripples through space-time and fling neutron-rich matter outward. Those mergers are now thought to be major sites for the creation of some very heavy elements, so the neutron star is not merely an exotic endpoint. It is also a forge, a reservoir, and a signal source. It affects what elements exist, what light and radiation we detect, and what gravitational wave events we can observe. That last point is especially lovely. When neutron stars collide, they do not simply vanish into a private astrophysical argument. They announce themselves across the universe. Gravitational waves spread outward, light of various kinds can follow, and in the matter hurled out during the event, rapid neutron capture can build heavy elements in abundance. So the gold in a ring or the rare metals in electronics may owe their existence, in part, to some ancient violent meeting of neutron-rich stars long before the Earth formed. The neutron thus links reactors on Earth, nuclei in laboratories, and collisions of collapsed stars in one continuous story. Even short of neutron stars, extreme neutron conditions shape more ordinary stellar evolution. In late stages of stellar burning and in explosive environments, neutron fluxes can become high enough to push nuclei into very unusual territory. The resulting isotopes may decay through chains that eventually settle into more familiar heavy elements. This reminds us that the periodic table is not a static list handed down complete at the beginning of time. It is the outcome of ongoing cosmic work. Neutrons are some of the main labourers in that work, especially when the conditions become intense. What makes all this so compelling is that the neutron seems at first like such a restrained idea. a neutral particle in the nucleus. That hardly sounds like the key to reactors, isotopes, stellar element formation, and collapsed stars. Yet once one follows what neutrality allows, the pattern becomes clear. Neutrons can enter nuclei. They can alter nuclear stability. They can trigger fission. They can be captured to build heavier isotopes. They can dominate matter under extreme compression. Their usefulness comes from a combination of access, mass, and transformability. They are easy for nuclei to admit, valuable to keep, and able through later weak processes to help matter change identity. There is also a practical philosophical lesson hiding in this. Extreme environments do not invent new physics from nothing. They reveal the consequences of ordinary physics pushed to unusual limits. The neutron in a reactor is still the same kind of particle as the neutron in a carbon nucleus, or the neutron in a beam experiment. The neutron in a neutron star is still connected to the same basic story of quarks, strong interaction, and weak transformation. What changes is the setting. In one place there are moderate densities and careful human control. In another there is a stellar collapse and gravity so severe that ordinary atomic structure can no longer survive. The particle is familiar. The world around it becomes extraordinary. Perhaps that is why neutrons feel so central once you have followed them far enough. They are not just another ingredient. They are one of the universe's main methods for handling complexity. They let nuclei become bigger than proton repulsion would otherwise permit. They allow heavy elements to be assembled through capture and later adjustment. They make controlled fission possible. They give rise to some of the densest objects known. They connect the quiet centre of the atom to the violent death of stars. Very few concepts in physics travel so smoothly from the modest to the extreme. And still, even with reactors humming, heavy elements forming, and neutron stars spinning out in the dark, the most curious fact remains almost the simplest one. All of this immense importance belongs to a particle that, by itself, cannot remain a neutron for very long. Alone, it decays. In nuclei, it helps hold matter together. In chains of fission, it keeps energy flowing. In cosmic foundries, it helps build the periodic table. In stellar ruins, it becomes the substance of an entire collapsed star. The neutron is temporary in solitude and indispensable in company, and that may be the clearest summary of its character. Which is why, after all this wandering through cores, reactors, heavy elements and collapsed stars, the particle begins to look less like a quiet extra and more like one of the great hidden coordinators of the material universe. It does not define the element the way the proton does. It does not dominate chemistry the way the electron does. But it determines which nuclei can last, which can grow, which can split, and what matter can become under pressure. Once you notice that, the neutron no longer seems like a side note in atomic structure. It starts to feel like one of the main reasons the universe has enough variety, enough drama, and enough durable substance to tell any story at all. And that may be the best way to understand the neutron in the end. Not as the dull middle companion of the proton, not as the grey circle in a textbook picture, and not even only as a particle that decays after a while when left on its own. The neutron makes the most sense when you see both sides of its character at once. It is the particle that helps matter hold together, precisely because it does not do very well in isolation. It is useful because it belongs in company. It becomes important because it fits into larger structures better than it survives by itself, and that is a very unusual sort of importance. Most of the time when we think about the basic pieces of nature, we expect the important ones to be the stable ones. We expect the strong, reliable ingredients to do the main structural work, rather like bricks in a wall or beams in a roof. There is a natural human preference for the dependable. We like the idea that the world is built from pieces that can look after themselves. The neutron gently refuses that preference. On its own, it is temporary. In the right company, it becomes one of the great enablers of durable matter. It is less like a brick carried alone in the hand, and more like the piece that makes the arch possible once the rest of the structure is in place. That already tells you something larger about physics. The world is not built only from isolated objects with fixed fates. It is built from relationships, environments, and balances. The neutron is stable in many nuclei not because its internal story suddenly changes, but because the surrounding structure makes remaining a neutron the better option. Outside the nucleus, the proton is the easier outcome. Inside many nuclei, the neutron is exactly what the system needs. That means stability is not simply a private property, it is often a shared one. And the neutron is one of the clearest examples of that truth anywhere in ordinary matter. It is worth looking once more at how much of the familiar world depends on this. The heavier nuclei around you do not exist because protons have somehow learned to tolerate being crowded together indefinitely. Protons repel one another electrically. That is not a small inconvenience, and it is not a detail that can be ignored with a brisk wave of the hand. The reason larger nuclei can exist is that neutrons join them and supply binding without adding more positive charge. They help create a compact, stable center for atoms that would otherwise struggle to hold together. Carbon, oxygen, silicon, calcium, iron, all these ordinary names belong to nuclei whose existence relies on neutrons doing exactly this quiet structural work. And the strange part is that the neutron can do that work so well only because of what it is internally. It is not an empty neutral lump. It is a composite particle made of quarks. It is close kin to the proton, similar enough to belong beside it in nuclei and different enough to matter. That tiny difference in internal composition gives it neutral charge overall and a slightly greater mass. The neutrality allows it to slip into nuclei without facing the same electrical resistance as a proton. The mass difference means that when it is free, it can eventually become a proton instead. So the very features that make the neutron useful in company are also the ones that make it temporary in solitude. There is something deeply satisfying in that arrangement, because it is so economical. The universe is not wasting effort here. The neutron is not some secondary afterthought added to patch a weakness in protons. It is a precisely tuned participant in the architecture of matter, close enough to the proton to form a natural pair, different enough to expand what nuclei can be, stable enough when bound to build the material world, unstable enough when free to take part in change. The neutron is not the odd spare part in the nucleus. It is the reason the nucleus has range. You can see that range everywhere once you start looking. In the early universe, free neutrons had only a short time to find a place in nuclei before decay thinned their numbers. That timing helps set the cosmic balance between hydrogen and helium. In stars, neutrons and neutron-related processes help determine how matter changes and what kinds of nuclei can be built. In the making of heavy elements, neutron capture gives nuclei a route upward through the periodic table that protons alone would have great difficulty providing. In reactors, free neutrons keep chain reactions alive by entering heavy nuclei and triggering fission. In neutron scattering laboratories, the same neutral particle becomes a subtle probe of matter, revealing structures that are otherwise hard to see. In neutron stars, matter itself is pushed into a state where neutrons dominate on a scale so extreme that ordinary language begins to wobble under the strain. The same particle appears in all of these stories, not as a decorative extra, but as a central actor. And yet if you tried to introduce it in the most brutally simple way possible, you might still be tempted to say something like, "This is the neutral particle in the nucleus," which is true in the same way that saying a library is a room with books is true. It is not wrong, but it leaves out almost everything that gives the thing its character. The neutron is not interesting because it lacks charge. It is interesting because neutrality lets it do things. It can join nuclei more easily. It can increase mass without increasing repulsion. It can be captured in ways that help elements grow. It can move through matter in experiments without being diverted like a charged particle. Neutrality is not the absence of a story. In the neutron, it is the beginning of one. That story also helps correct a habit people often have when learning science, which is the habit of sorting everything into a main thing and a support thing. Protons sound main because they define the element. Electrons sound main because chemistry depends on them. Neutrons can sound like support staff, useful perhaps, but not central. Once you have followed the neutron through nuclear stability, decay, reactors, element formation, and stellar collapse, that ranking starts to look much less convincing. Protons may name the element, electrons may govern chemistry, but neutrons determine whether complex nuclei can exist in the first place, and what kinds of nuclear lives those elements can lead. That is not background work. That is structural work in the deepest sense. There is also a quiet lesson here about what it means to hold something together. We tend to imagine holding together as a matter of strength, of resisting change, of being unmoved. The neutron shows a different version. It holds matter together not by being the most unchangeable particle around, but by fitting into collective structures that need exactly what it offers. It is not holding the nucleus together by standing in the middle like an angry referee. It is holding it together by contributing to binding while not making electrical repulsion worse. It is helping because it participates in the right way. Its usefulness is relational. That is what makes the phrase refusing to last alone feel less like a poetic trick and more like a plain statement of the physics. A free neutron, after all, has limited prospects. It can travel for a while, it can be measured, it can interact, it can be captured by a nucleus if one is willing to have it. But if nothing captures it, if it remains genuinely alone, then the weak interaction gives it a lawful path toward becoming a proton. The neutron does not endure indefinitely in solitude because solitude removes the larger structure that could justify its extra mass. There is no nucleus around for it to stabilize, no proton crowd needing quiet assistance, no binding energy to reward its presence. It is simply itself, and in that condition nature prefers the slightly lighter outcome. Inside a nucleus, the picture changes completely. Now the neutron belongs to a shared arrangement. Its presence can lower the energy of the system as a whole. Its absence or transformation might make the nucleus less stable rather than more. That is why many bound neutrons survive for extraordinary spans of time. They are not being exempted from the laws that govern free neutrons. They are living under the full accounting of the nucleus. The system wants them there. The home suits them, and because it suits them, matter itself can become richer, heavier, and more durable. That idea of home has been useful all along because it turns a technical fact into something easier to feel without making it less true. Home is the place where something fits naturally and remains itself with less strain. For the neutron, the nucleus is often exactly that. Not always, since some nuclei are unstable and do rearrange themselves, but often enough that most of the ordinary world around us is built from neutrons that have found just such a place. The stone in an old wall, the oxygen in the air, the calcium in teeth, the iron in the earth, all contain neutrons that are not free to decay because the nuclei they inhabit would not be improved by losing them or turning them into protons. That is one of the reasons the world can be ordinary at all. It is also one of the reasons the neutron feels oddly modest. It does all this without taking the public credit. People rarely say what a beautiful evening, let us all be grateful for neutrons. That is not how ordinary thought works. We notice surfaces, colours, objects, living things, weather, and perhaps on a scientific evening the occasional star. We do not usually pause at dinner to consider the quiet nuclear bookkeeping that allows the table, the cutlery, the food, and our own bones to exist in their present form. The neutron is part of the hidden support system of reality. It does not advertise, it enables. And perhaps that is why it ends up being so satisfying as a topic. There is a kind of scientific pleasure in finding that the apparently modest thing is not modest at all. The neutron begins as a simple answer to a school question and ends as a guide to some very deep ideas. It teaches that particles can be composite. It teaches that stability depends on context. It teaches that tiny mass differences can shape the large-scale universe. It teaches that neutral does not mean empty, and that temporary does not mean unimportant. It teaches that the material richness of the world depends on a particle whose role only becomes fully clear when it is surrounded by others. This is one place where the older textbook diagrams, for all their limitations, almost deserve a little forgiveness. They were trying to tell the truth in a simple way. The nucleus does contain protons and neutrons. That is a good place to begin. It just is not a good place to stop. The real picture is more lively. The proton and neutron are near relatives with different fates. The neutron contributes binding without charge. It can decay when free but remain stable when bound. It can be captured to help build heavier nuclei. It can drive fission, reveal material structure, and dominate collapsed stars. The neat little diagram survives, but behind it there is an entire world of interaction and consequence. If anything, the neutron improves with familiarity. Many scientific ideas feel hardest when first encountered, and then become routine once the basic facts are memorized. The neutron does the opposite. At first it sounds simple, then the more familiar you become with it, the more subtle it appears. You learn that it is made of quarks. You learn that most of its mass comes from internal energy. You learn that it has magnetic character despite no net charge. You learn that its lifetime when free is finite and measurable. You learn that inside nuclei it may be stable or unstable, depending on the full nuclear arrangement. You learn that it helps build the elements and powers reactors and forms stars that are not really stars anymore in any ordinary sense. It keeps becoming more interesting. There is also something quite reassuring about the way the neutron ties together different scales of explanation. One can speak about quarks and the weak interaction, and one is talking about the neutron. One can speak about carbon nuclei and isotopes, and one is still talking about the neutron. One can speak about the abundance of helium after the first minutes of the universe, or about the formation of gold in violent cosmic events, or about the operation of a reactor core, and the neutron remains right there in the center of the explanation. Few ideas travel so well from the smallest scale to the largest. That gives the particle a kind of unity. It belongs everywhere that matter is trying to become more than the simplest possible version of itself. And that, perhaps, is the cleanest way to say why the neutron matters. The proton gives matter identity. The electron gives matter chemistry. The neutron gives matter complexity. It allows nuclei to grow beyond the smallest cases. It lets heavy elements exist. It permits a rich periodic table instead of a very short one. It lets matter be stable in more ways than charge alone would allow. And it does all this while carrying within itself a quiet warning that on its own it would not remain what it is forever. Complexity, in the neutron, is made possible by a particle that only really comes into its full usefulness in community. There is a gentle irony in that. The neutron is temporary when alone, but when gathered into nuclei it becomes part of things that can last for billions of years. Entire mountains depend on it. Planets depend on it. Long-lived stars and short-lived stars both depend on it in different ways. Life depends on it because life depends on heavy elements and stable nuclei. The neutron itself does not last alone, yet by refusing to last alone it becomes part of the most durable structures we know. It gives up independence and gains significance. That is a very peculiar sort of success, but a real one. So when you come back to the original question, what is a neutron? The answer is no longer just that it is a neutral particle in the atomic nucleus. It is a composite hadron made of quarks. It is the close relative of the proton that is slightly heavier and therefore unstable when free. It is the quiet contributor that helps nuclei hold together without adding electrical strain. It is the route by which heavy elements grow. It is the traveller that can enter nuclei, trigger fission, and probe matter. It is the particle that can become a proton through the weak interaction, and the particle that can, in overwhelming numbers, form the body of a collapsed star. Above all, it is a reminder that the universe is built not only from things that endure alone, but from things whose meaning appears most clearly in the structures they help create. And if there is a final comfort in that, it is not a mystical one. It is simply the comfort of seeing that the world makes more sense once you look closely enough. The neutron seemed at first like the least interesting resident of the atom. By the end it turns out to be one of the reasons the atom can become a world, and one of the reasons the world can become stars, planets, metals, water, air, bones, blood, stone, and all the rest of the ordinary miracle we rarely pause to examine. The neutron does not last alone, and because it does not, matter itself can last in forms rich enough for us to notice, study, and quietly admire.